Perhaps the most surprising thing about the ancient world is that it often feels less mysterious after a discovery, and then more mysterious the longer it is studied. A newly uncovered ruin may initially seem straightforward. Archaeologists identify its age, map its layout, and connect it to a known culture. Case closed. But years later, unexpected details begin to emerge. Construction methods that should not work, designs that appear ahead of their time, features that do not match the accepted explanation. Slowly, certainty begins to unravel. This pattern repeats across the world. From forgotten cities to famous monuments, the deeper researchers investigate, the more they encounter questions that were never part of the original discovery. And that is why ancient mysteries endure. They're not created by a lack of evidence, but by evidence that refuses to fit neatly into the story. Tassili N'Ajjer lies in the remote sandstone plateaus of southeastern Algeria, deep within the Central Sahara. More than 15,000 prehistoric paintings and engravings cover its cliffs, shelters, and stone corridors, preserving a visual record that spans nearly 10,000 years. Yet the greatest mystery of Tassili is not what these ancient artists painted. It is how they achieved levels of environmental knowledge, artistic sophistication, and material technology that continue to challenge modern explanations. The modern world first became aware of Tassili's significance during the 20th century when French explorer and archaeologist Henri Lotte conducted major expeditions across the region between the 1950s and 1970s. What researchers initially expected to be isolated examples of rock art quickly revealed itself as one of the largest prehistoric archives ever discovered. Stretching across roughly 72,000 square kilometers, the plateau contains thousands of decorated sites. The sheer scale alone is astonishing. Even today, archaeologists continue to identify previously undocumented artworks hidden among the maze-like sandstone formations. The first mystery emerged from the images themselves. Today, Tassili lies within one of the driest environments on Earth. Annual rainfall is often measured in only a few centimeters, and summer temperatures can exceed 45 degrees Celsius. Yet the paintings depict an entirely different world. Hippopotamuses appear swimming in rivers, crocodiles inhabit lakes, herds of elephants, giraffes, antelope, and cattle move across grasslands. Modern climate science now confirms that between approximately 11,000 and 5,000 years ago, the Sahara experienced what researchers call the African humid period. During this era, monsoon systems expanded northward, transforming vast regions of desert into savannas, wetlands, and seasonal lakes. What is remarkable is that the artists of Tassili effectively recorded this environmental transformation thousands of years before modern geology, sediment analysis, and satellite imaging proved it scientifically. The paintings function almost like a prehistoric climate database. Different artistic phases document changing animal populations and human lifestyles over thousands of years. Early paintings emphasize wild fauna associated with humid environments. Later images increasingly feature domesticated cattle. Eventually, horses and camels appear as arid conditions intensified. The sequence corresponds closely with modern paleoclimatic reconstructions derived from lake sediments and pollen records. This raises an intriguing question. How did societies without writing preserve environmental knowledge across dozens of generations with such accuracy? Another mystery involves the famous roundhead paintings, among the most enigmatic works ever found in prehistoric art. Dating roughly between 8,000 and 6,000 years ago, these figures differ dramatically from most known hunter-gatherer representations. Human forms appear with enormous circular heads, elongated bodies, and seemingly floating poses. Some figures reach several meters in height. The most famous example, often called the Great God of Safa, stands over 5 meters tall. While popular culture has frequently associated these images with extraterrestrial theories, archaeologists reject such interpretations. The real mystery is far more fascinating. The artist demonstrated an ability to create visual depth, complex compositions, and abstract symbolism rarely seen in prehistoric rock art elsewhere. When compared with the cave paintings of Lascaux in France or Altamira in Spain, Tassili's roundhead tradition appears uniquely experimental. The figures often lack anatomical realism but display sophisticated symbolic structure. Some scenes suggest ritual activities, altered states of consciousness, or ceremonial gatherings. Yet no surviving texts exist to explain their meaning. Researchers can analyze pigments, estimate dates, and reconstruct cultural contexts, but the symbolic language itself remains largely undeciphered. Perhaps the most astonishing mystery concerns the pigments. Thousands of years after their creation, many paintings still preserve vivid shades of red, yellow, brown, black, and occasionally white. Under normal circumstances, exposure to heat, ultraviolet radiation, wind erosion, and temperature fluctuations should have destroyed much of the artwork long ago. Instead, significant portions remain remarkably visible. Scientific analysis reveals that many pigments were derived from naturally occurring minerals. Red colours often originated from iron oxides such as hematite. Black pigments frequently contain manganese compounds. Yellow and brown tones were produced using various mineral-rich clays and ochres. However, minerals alone cannot fully explain the extraordinary durability of the paintings. Pigments generally require binders to adhere effectively to rock surfaces. Researchers suspect that prehistoric artists mixed mineral powders with organic substances such as plant resins, animal fats, blood, egg proteins, or tree gums. The problem is that most organic compounds degrade over time, leaving only fragmentary chemical traces. Even with modern laboratory techniques, scientists have not completely reconstructed the original formulas. Some analyses suggest sophisticated mixtures capable of enhancing adhesion, increasing resistance to weathering, and improving color stability. Comparisons with ancient Egyptian pigments reveal an interesting contrast. Egyptian wall paintings survived largely because they were protected inside tombs. Tassili paintings endured while exposed to an open-air desert environment for millennia. Understanding precisely how these pigments achieved such longevity remains one of the most important unanswered questions in archaeological material science. The mystery becomes even deeper when considering the locations of many artworks. Numerous paintings are positioned high on vertical rock faces, inside elevated shelters, or within difficult-to-access chambers. Modern researchers often require climbing equipment to reach some of these areas, yet the original artists somehow transported pigments, tools, water, and supplies across rugged terrain without modern technology. No wooden scaffolding survives because organic materials rapidly decompose in harsh environments. Consequently, archaeologists possess little direct evidence regarding the construction methods used to access these locations. Did prehistoric communities develop elaborate rope systems? Did they build temporary platforms from imported timber? Or were environmental conditions different enough to make access easier thousands of years ago? Definitive answers remain elusive. Equally mysterious is the apparent organization behind the creation of so much artwork. Producing a single large painting requires planning, pigment preparation, labor, and technical knowledge. Producing thousands of paintings across tens of thousands of square kilometers implies extensive cultural networks. The scale rivals some of the largest artistic traditions in prehistory. Yet, Unlike civilizations such as Egypt or Mesopotamia, the people of Tassili left no written records explaining how their knowledge was transmitted. Researchers increasingly believe that the Sahara during the African humid period supported interconnected populations linked through trade routes, migration corridors, and shared ceremonial traditions. Similar artistic motifs appear across regions separated by hundreds or even thousands of kilometers. This suggests the existence of communication networks far more sophisticated than once imagined. The challenge is understanding how information spread so effectively across vast landscapes before the emergence of formal states. The geological setting adds another layer to the puzzle. Much of Tassili consists of spectacular sandstone formations sculpted by erosion into arches, towers, corridors, and labyrinths. Some areas, particularly around Sifar, resemble an abandoned stone metropolis. Researchers suspect that these formations created unique microclimates that helped preserve artworks. Rock shelters may have reduced exposure to sunlight, wind, and rainfall, while stabilizing temperature fluctuations. Yet preservation patterns vary dramatically even between neighboring sites, indicating that additional factors remain poorly understood. Modern technology has revolutionized the study of Tassili. Tools such as satellite imagery, drones, and chemical analysis reveal details once unseen. Yet many mysteries remain. Scientists can identify pigments and date paintings, but they still cannot fully explain their durability, symbolism, or the societies that created them. What do you think was the secret behind Tassili's remarkable pigment technology and lost knowledge? Share your thoughts in the comments below. Marago Island sits at the mouth of the Amazon River in northern Brazil. At first glance, it seems like an unlikely place for one of the most sophisticated ancient societies in South America. Vast seasonal floods, waterlogged soils, tropical heat and dense vegetation should have made large-scale urban development nearly impossible. Yet beneath the forests and grasslands of Marajo Island lies evidence of a civilization that flourished for nearly 1,000 years and developed engineering solutions that continue to puzzle archaeologists today. The existence of the Marahora culture became widely known during the 19th century when explorers and researchers began documenting enormous artificial mounds scattered across the island. What initially appeared to be natural hills turned out to be massive human-made structures. Excavations later revealed complex settlements, elaborate burial urns, sophisticated ceramics, and evidence of large populations occupying a landscape once believed incapable of supporting advanced societies. The discovery challenged one of the longest-standing assumptions in Amazonian archaeology, that the rainforest could only sustain small, scattered communities. The first mystery begins with the monumental earthworks themselves. Across Marajo Island stand hundreds of artificial mounds known as tezos. Some rise more than 10 meters above the surrounding floodplain and extend for hundreds of meters. Archaeologists estimate that many contain tens of thousands of cubic meters of earth. The question is not simply why they were built, but how. Unlike the stone pyramids of Egypt or the masonry cities of the Andes, these structures were constructed entirely from soil in one of the wettest environments on Earth. During seasonal floods, large portions of the island become inundated. Under such conditions, earthen constructions normally erode rapidly. Yet many Marahora mounds survived for centuries and remain visible today. Researchers believe these platforms served multiple purposes. They elevated villages above floodwaters, provided ceremonial spaces, and may have functioned as political centers. However, constructing them required moving enormous quantities of sediment without draft animals, wheeled vehicles, or metal tools. Comparisons are often made with the mound-building cultures of North America, such as Cahokia, where labourers also transported vast amounts of earth by hand. Yet the environmental challenges on Morejo were arguably even greater, because builders worked within a dynamic floodplain that constantly changed shape through erosion and sediment deposition. Modern engineering projects frequently struggle to maintain stable foundations in such environments. The Mara Hora managed to do so more than 1,000 years ago. The deeper archaeologists investigated these earthworks, the more evidence emerged suggesting that the mounds were only part of a larger environmental engineering system. Surveys revealed networks of raised fields, canals, reservoirs, and modified landscapes extending across wide areas. Rather than adapting passively to the environment, the Mara Hora appear to have reshaped it. Some researchers describe the island as a form of engineered ecosystem, where human intervention altered water flow, agricultural productivity, and settlement patterns on a regional scale. This raises another unresolved question. How did the Mara Hora understand the hydrology of one of the world's largest river systems so well? Seasonal flooding in the Amazon can vary dramatically from year to year. Water levels fluctuate, channels migrate, and landscapes transform. Yet evidence suggests that Mara Hora settlements were strategically positioned to exploit these changes rather than suffer from them. Certain canals may have functioned as transportation routes during wet seasons and as fish management systems during dry periods. Similar hydraulic achievements are often associated with civilizations such as the ancient Khmer at Angkor or the engineers of Mesopotamia. The difference is that those societies left extensive monuments and written records. The Mara Hora left neither, making their technical knowledge far more difficult to reconstruct. Perhaps the greatest mystery of all involves a substance that continues to fascinate soil scientists around the world: terra preta, or Amazonian dark earth. For centuries, explorers noticed patches of unusually fertile black soil scattered throughout parts of the Amazon basin. These areas often contained archaeological remains, suggesting a connection to ancient human activity. Scientific analysis eventually revealed that terra preta is not a natural soil. It was deliberately created. This discovery transformed understanding of Amazonian history. Most Amazonian soils are highly weathered and nutrient-poor. Heavy rainfall rapidly washes away essential minerals, making long-term agriculture difficult. Terra preta behaves differently. It contains extraordinary concentrations of organic matter, charcoal, phosphorus, calcium, nitrogen, and beneficial microorganisms. Even after hundreds or sometimes thousands of years, it remains significantly more fertile than surrounding soils. The engineering implications are astonishing. Studies have shown that terra preta can contain several times more carbon than nearby natural soils. Some samples exhibit fertility levels capable of supporting intensive agriculture long after their original creators disappeared. Modern scientists have attempted to reproduce its properties using biochar and other techniques, yet many characteristics of terra preta remain difficult to duplicate fully. The exact combination of organic waste, charcoal production, microbial activity, and long-term management that created these soils is still debated. For the Mara Hora, terra preta may have been the foundation of everything. A large population requires reliable food production. Earlier theories argued that Amazonian societies could never achieve significant demographic growth because the rainforest environment imposed strict agricultural limits. Terra preta challenges that assumption directly. If the Mara Hora mastered large-scale soil enhancement, they may have overcome one of the greatest environmental obstacles in tropical agriculture. Some scholars have even suggested that Amazonian peoples were practicing a form of sustainable ecological engineering centuries before comparable concepts emerged in modern science. The mystery deepens because Terra Preta appears across different regions of the Amazon rather than in a single isolated location. This raises difficult questions about knowledge transmission. Was the technology independently invented multiple times? Did trade networks spread the technique across vast distances? Or did a broader tradition of environmental engineering exist throughout prehistoric Amazonia? No consensus has yet emerged. The ceramics of the Marajora provide another clue to their sophistication. Archaeologists regard Marajoara pottery as among the finest ever produced in pre-Columbian South America. Intricate geometric patterns cover large funerary urns, ceremonial vessels, and sculptural objects. The complexity of the design suggests specialized artisans and highly developed manufacturing traditions. Some urns display extraordinary symmetry and precision, despite being created without modern tools. The production process itself remains only partially understood. Potters needed access to suitable clay sources, controlled firing conditions, pigment preparation techniques, and systems for transmitting artistic knowledge across generations. In many civilizations, such specialization emerges only when societies possess sufficient agricultural surpluses to support full-time craftsmen. If that was also true on Marajo, then the underlying economic system must have been far more complex than previously imagined. Population estimates remain uncertain, but some researchers suggest that tens of thousands of people lived on Marajo Island at the peak of Marajoara society. Even lower estimates indicate strong social organization, requiring effective resource management and coordination. Unlike the Inca, Maya, or Romans, however, the Marajoara left no known writing system to reveal how their society functioned. The final mystery concerns decline. Around the 14th century, many major Marajoara centers appear to have been abandoned or transformed. Archaeologists have proposed climate fluctuations, environmental change, political instability, disease, and resource stress as possible explanations. None fully accounts for the available evidence. Like the collapse of the classic Maya cities or the decline of Cahokia in North America, the disappearance of Marajoara complexity remains incompletely understood. How did the Marajoara create Terra Preta and build such a complex society in the heart of the Amazon? Let us know your theory in the comments below. Monte Alegre State Park lies on the northern bank of the Amazon River in Para, Brazil. Hidden among isolated sandstone hills rising above the rainforest are traces of a civilization whose technological abilities continue to challenge modern explanations. The mystery first emerged when archaeologists began systematic investigations of caves and rock shelters in the region during the late 20th century. Excavations at Pedra Pintada and neighboring sites revealed stone tools, ancient hearths, food remains, and rock paintings associated with human occupation dating back more than 11,000 years. These discoveries shocked researchers because they contradicted long-standing theories that the Amazon was settled relatively late and lacked complex prehistoric cultures. Instead, Monte Alegre suggested that sophisticated communities were already thriving near the end of the Ice Age. What makes Monte Alegre remarkable is not the presence of ancient people alone. The true mystery lies in the advanced knowledge systems hidden behind the surviving evidence. The site presents a combination of astronomical observation, landscape engineering, artistic technology, environmental adaptation, and information preservation that remains only partially understood. Among the most intriguing puzzles is the apparent relationship between the rock formations and the sky. Several archaeological investigations have identified locations where sunlight passes through natural openings or illuminates specific sections of rock surfaces during particular times of the year. Some researchers have suggested that certain markings may correspond to seasonal solar events such as solstices. If this interpretation is correct, the implications are extraordinary. Measuring the annual movement of the sun requires repeated observations over many years. Even a small error can shift predicted alignments by significant distances. Ancient observers would have needed a deep understanding of horizon markers, seasonal cycles, and solar motion. Similar astronomical discussions surround famous sites such as Stonehenge in England and Chanquillo in Peru, both regarded as among the earliest known solar observation complexes. Yet Monte Alegre predates many of these traditions, raising difficult questions about how much astronomical knowledge existed in prehistoric Amazonia. The challenge becomes even greater when the geography of the region is considered. The sandstone hills surrounding Monte Alegre provide commanding views across vast portions of the Amazon basin. From elevated points, ancient inhabitants could observe river systems, migration routes, seasonal flooding patterns, and celestial events. Some archaeologists argue that selecting these locations required a sophisticated understanding of landscape surveying. Without maps, compasses, or modern instruments, people consistently chose positions that maximize visibility and strategic advantage. Such decisions suggest a level of environmental planning far beyond simple survival. The rock art itself presents another engineering mystery. Hundreds of paintings are distributed across cliffs, shelters, and cave walls. Many are located in positions that remain difficult to access even today. Some paintings appear on steep rock faces several meters above the ground. Creating them would likely have required temporary platforms, climbing systems, scaffolding, or carefully designed support structures. Yet the humid tropical environment rapidly destroys organic materials, leaving little direct evidence behind. Researchers therefore face an unusual problem. The artwork survives, but the technology used to create it has vanished. The most fascinating puzzle involves the pigments themselves. Many of the paintings retain visible coloration despite exposure to thousands of years of environmental stress. In an ecosystem characterized by intense rainfall, extreme humidity, biological activity, and fluctuating temperatures, long-term pigment preservation should be exceptionally difficult. Nevertheless, red paintings remain visible across multiple sites throughout Monte Alegre. Scientific analyses indicate that iron oxide was likely a primary component of the red pigment. Iron oxide is common in prehistoric art around the world and was also used at sites such as Lascaux in France and Altamira in Spain. However, mineral colorants alone do not automatically survive for millennia. They require adhesion to rock surfaces and resistance to chemical degradation. This is where the mystery begins. Researchers suspect that prehistoric artists may have mixed iron-rich minerals with organic binding agents derived from plants, tree resins, oils, animal fats, or other natural compounds. Such mixtures could have increased durability and resistance to weathering. The problem is that most organic ingredients decompose over time, making precise reconstruction extremely difficult. Despite advances in microscopy, spectroscopy, and chemical analysis, scientists still cannot fully reproduce the exact formulation that allowed some Monte Alegre pigments to remain visible for more than 10,000 years. The scale of this achievement becomes clearer through comparison. Many historical paints used in medieval structures survive only a few centuries before requiring restoration. Modern outdoor pigments frequently deteriorate within decades when exposed to harsh environmental conditions. Yet some Monte Alegre paintings have persisted since the closing stages of the Pleistocene. The durability suggests an unexpectedly sophisticated understanding of material properties, whether developed intentionally through experimentation or accumulated through generations of practical knowledge. Equally puzzling is the consistency of pigment performance across different locations. If the artists were using locally gathered minerals, they must have possessed methods for identifying suitable deposits, processing raw materials, controlling particle size, and preparing mixtures capable of bonding effectively to stone surfaces. These are not random actions. They represent a chain of technical decisions comparable in principle to early chemical engineering. The environmental challenges faced by Monte Alegre's inhabitants create another layer of mystery. Around 11,000 years ago, the Amazon basin was undergoing significant climatic transitions associated with the end of the last ice age. Ecosystems were changing, river systems were shifting, and vegetation patterns were evolving. Maintaining stable communities under such conditions would have required detailed ecological knowledge. Archaeological evidence indicates that inhabitants exploited diverse food sources, including fish, fruits, nuts, and terrestrial animals. Managing these resources across changing environments suggests an advanced understanding of seasonal cycles and landscape productivity. This adaptability challenges traditional assumptions about prehistoric Amazonian populations. For decades, scholars often portrayed early Amazon communities as small, isolated groups limited by environmental constraints. Monte Alegre increasingly points toward a different picture. The evidence suggests people capable of organizing labor, transmitting knowledge across generations, and mastering complex environmental systems. Their achievements were not expressed through monumental stone pyramids or massive cities. Instead, they were embedded within observation material science, ecological management, and symbolic communication. The geometric motifs found among the paintings deepen the mystery further. Alongside depictions of humans and animals are circles, grids, zigzags, and abstract patterns whose meanings remain uncertain. Some researchers interpret them as symbolic representations of cosmological concepts. Others propose that they functioned as territorial markers, information systems, or mnemonic devices. A few have even suggested possible relationships to seasonal observations. No consensus exists. What is striking, however, is that such abstract imagery appears repeatedly across large areas of South America, hinting at intellectual traditions far more complex than once believed. Charles Fort stands above the entrance to Kinsale Harbour in Southern Ireland. From the air, its vast star-shaped geometry appears almost impossible for the 17th century. More than 3 centuries after its construction, the fortress remains one of the most sophisticated military engineering achievements ever built in the British Isles, raising questions that historians, architects, and engineers still debate today. The site was documented continuously since its construction between 1677 and 1682 under the supervision of military engineer William Robinson. Unlike many ancient mysteries rediscovered after centuries of abandonment, Charles Fort was never truly lost. Yet modern aerial photography revealed something that observers on the ground could never fully appreciate. The fortress was not merely a collection of walls, it was a gigantic mathematical machine built into the landscape itself. Only when viewed from above did researchers realize the extraordinary precision hidden within its geometric design. What makes Charles Fort fascinating is that its greatest mysteries are not about who built it or when it was built. Historical records answer those questions. The deeper mystery is how engineers operating without computers, satellites, laser surveying equipment, or modern structural analysis created a defensive system whose efficiency continues to impress military experts centuries later. The first puzzle emerges from the fortress's overall geometry. Charles Fort covers approximately 11 hectares and follows the principles of the Star Fort, a revolutionary military design that spread across Europe during the age of gunpowder. At first glance, the shape appears decorative, but every angle serves a mathematical purpose. Traditional medieval castles relied on tall walls, Once artillery improved, those walls became liabilities because cannon fire could shatter them. Star forts represented a completely different solution. Instead of height, they used geometry. The bastions projecting outward from Charles Fort create overlapping fields of fire that eliminate blind spots around the walls. Military simulations conducted on similar star forts demonstrate that attackers approaching almost any section of the defences would be exposed simultaneously from multiple directions. This concept resembles modern military doctrines of interlocking defensive zones. Yet, 17th century engineers had no digital models to calculate thousands of possible firing trajectories. They relied entirely on geometry, measurement, and practical experience. Historians still debate the exact methods used to calculate these relationships across such a large area with remarkable consistency. The fortress also presents a mystery concerning energy absorption and structural resilience. Most people assume defensive strength comes from thicker stone walls. Charles Fort reveals a more sophisticated principle. Its walls are relatively low compared to medieval castles, but they are supported by massive earthworks hidden behind masonry facades. Modern engineering recognizes that compacted earth absorbs shock waves far more effectively than solid stone alone. When artillery projectiles strike a rigid wall, energy concentrates at the point of impact. When earth embankments support the structure, much of that energy disperses through the surrounding mass. This principle resembles concepts used in modern blast-resistant construction. The remarkable question is how engineers understood these effects long before the science of stress analysis, material mechanics, and impact physics existed. Their knowledge emerged from centuries of experimentation rather than mathematical theory. Much of that practical understanding was never formally recorded, leaving researchers with structures that work extraordinarily well, but without complete explanations of how builders optimized them. The landscape itself introduces another engineering mystery. Charles Fort occupies a steep coastal position overlooking Kinsale Harbour. Building on such terrain creates numerous challenges even today. Uneven ground can cause differential settlement, wall deformation, drainage failures, and long-term instability. Modern projects typically depend on geological surveys, computer models, and extensive soil analysis before construction begins. Yet the builders of Charles Fort successfully integrated the fortress into a complex sloping environment while maintaining geometric coherence across the entire structure. Bastions align correctly, defensive angles remain consistent, drainage continues to function centuries later. The engineering challenge resembles constructing a giant geometric instrument across an irregular natural surface. Researchers studying the site often note that the design adapts to the landscape rather than forcing the landscape to conform entirely to the design. This flexibility may explain part of the fortress's remarkable longevity, but exactly how surveyors translated geometric plans into physical reality remains only partially understood. Water management presents another puzzle. Coastal fortifications face constant threats from rainfall, groundwater movement, erosion, and salt exposure. Over centuries, water often destroys military structures more effectively than warfare itself. Archaeological investigations indicate that Charles Fort incorporated sophisticated drainage systems throughout its design. Rainwater could be directed away from vulnerable foundations, while earthworks remained stable despite Ireland's wet climate. The effectiveness of these systems becomes obvious when compared with many contemporary fortifications that suffered severe structural deterioration. Engineers today understand the importance of drainage, but what continues to impress researchers is how comprehensively water control was integrated into the original design. The fortress was conceived as a living hydraulic system as much as a military installation. Every slope, ditch and embankment contributed to directing water away from critical structures. The greatest mystery of all revolves around surveying precision. This is where Charles Fort becomes truly extraordinary. Modern surveyors use GPS satellites, total stations, laser scanners, drones, and digital mapping software capable of measuring positions to within centimeters or even millimeters. The engineers of Charles Fort possessed none of these tools. Nevertheless, they produced a fortress whose geometric relationships remain astonishingly accurate across an area larger than many medieval towns. The bastions align according to carefully calculated angles. Defensive lines maintain consistent proportions. Observation points command strategic views of the harbour entrance. Artillery positions maximize coverage while minimizing vulnerabilities. Every element depends on precise measurement. To appreciate the scale of this achievement, consider that a small angular error introduced during initial surveying would multiply dramatically across hundreds of meters. By the time construction reached the outer defenses, tiny mistakes could become major distortions. Yet, Charles Fort displays a degree of geometric coherence, suggesting exceptionally advanced surveying practices. Researchers believe the engineers relied on triangulation methods, astronomical observations, chains, measuring rods, compasses, and optical instruments available during the 17th century. Triangulation remains a foundation of modern surveying, but implementing it across a complex coastal landscape required extraordinary skill. The mystery is not that the methods existed. The mystery is how effectively they were applied. Some historians argue that military engineers of the period possessed practical surveying abilities far beyond what most people imagine today. Comparisons with other famous star forts strengthen this mystery. Fortifications such as Pulmanova in Italy and Naarden in the Netherlands exhibit similar geometric sophistication. Yet Charles Fort occupies far more challenging terrain than many continental examples. Achieving comparable precision on an uneven coastal site magnifies the engineering accomplishment considerably. More than 340 years after construction, Charles Fort continues to withstand Atlantic storms, coastal erosion, seasonal temperature changes, and the effects of war. Portions of the fortress were damaged during the Irish Civil War in 1922, yet much of the original defensive system survives. Its endurance provides powerful evidence that the engineers understood their environment at an exceptionally deep level. What do you think was the most impressive achievement of Charles Fort's engineers? Share your thoughts in the comments below. Lalitgiri, isolated on a low hill range in Odisha, eastern India, appears at first glance to be another ruined Buddhist monastery. Yet beneath its weathered bricks lies one of the most puzzling engineering stories in ancient South Asia. Archaeologists uncovered evidence of a major Buddhist center dating from roughly the 1st century BC to the 13th century AD, making Lalitgiri one of the oldest Buddhist complexes in India. What transformed the site from an ordinary excavation into an archaeological mystery was not merely its age, but the discovery of advanced construction techniques, unusually durable materials, sophisticated planning, and perhaps most intriguingly, a series of stone relic caskets crafted with a level of precision that continues to raise questions about the technological capabilities of the people who built them. The modern rediscovery of Lalitgiri began during archaeological surveys of Odisha in the 20th century. Systematic excavations conducted by the Archaeological Survey of India eventually revealed a massive monastic complex, a large brick stupa, dozens of smaller votive stupas, sculptures, inscriptions, and one of the most important finds ever made at a Buddhist site in India. A relic chamber containing nested stone containers believed by some scholars to have held sacred Buddhist relics. As excavation expanded, researchers realized that Lalitgiri was not an isolated monastery. It formed part of a vast Buddhist network together with Ratnagiri and Udayagiri, creating a regional religious and educational landscape that flourished for centuries. Yet every new discovery seemed to generate even more difficult questions. The first puzzle emerges from the location itself. Lalitgiri occupies elevated terrain overlooking the surrounding plains. Modern visitors can reach the hill with relative ease, but transporting construction materials there nearly 2,000 years ago would have been a very different challenge. Archaeologists estimate that the principal stupa and associated structures required hundreds of thousands of bricks. Even if each brick weighed only 2 to 4 kilograms, the total mass of material transported uphill would have reached hundreds or even thousands of tons. Similar logistical challenges have been documented at sites such as Nalanda and Sanchi, but Lalitgiri presents an additional complication. Evidence suggests multiple phases of expansion over several centuries, meaning construction was not a single event but a continuous process requiring stable supply chains, labor organization, and engineering knowledge. No written records survive to explain how this logistical system operated. The durability of the brickwork presents another mystery. Many ancient brick structures across tropical South Asia have suffered severe deterioration from monsoon rains, biological growth, thermal stress and erosion. Yet substantial portions of Lalitgiri survived for more than a millennium. Laboratory analysis of ancient Indian bricks has demonstrated compressive strengths that sometimes approach or exceed those of certain modern fired bricks. Researchers believe ancient craftsmen carefully selected clay sources and controlled firing temperatures, but the exact production methods remain uncertain. Unlike modern brick manufacturing, which relies on standardized industrial kilns and temperature monitoring systems, ancient builders achieved remarkable consistency using technologies that remain only partially understood. The survival of these structures becomes even more impressive when compared with many later medieval buildings that deteriorated more rapidly despite having access to more advanced tools. Water management may represent an even greater engineering achievement. Odisha receives significant seasonal rainfall, often exceeding 1,400 millimeters annually. Any large hilltop complex exposed to centuries of monsoon activity faces constant threats from runoff, erosion, and foundation instability. Modern engineers combat such problems using drainage calculations, hydrological models, and reinforced foundations. Lalitgiri's builders possessed none of these technologies, yet the archaeological record indicates that the site remained functional through countless monsoon cycles. Excavations have identified drainage channels and evidence of carefully planned water control systems, but researchers still struggle to reconstruct the complete hydraulic network. The unanswered question is whether surviving features represent only a small fraction of a much larger engineering system that has since disappeared. The mystery becomes deeper when examining the broader architectural planning of the complex. The layout of monasteries, shrines, pathways, and stupas suggests deliberate organization rather than gradual random growth. Ancient builders appear to have balanced religious symbolism with practical concerns such as circulation, visibility, drainage, and structural stability. Comparable planning can be observed at major Buddhist centers like Nalanda, yet Lalitgiri's elevated terrain imposed additional constraints. Modern archaeological mapping reveals alignments and spatial relationships that imply careful surveying methods. The challenge is understanding how such measurements were performed. Without modern optical instruments, laser levels, or standardized engineering equipment, ancient surveyors still managed to create a coherent architectural landscape capable of functioning for centuries. Among all these mysteries, however, None is more fascinating than the relic caskets discovered within the stupa complex. These objects transformed Lalitgiri from an important archaeological site into a genuine technological puzzle. The relic chamber contained multiple nested containers fashioned from stone with remarkable craftsmanship. At first glance, the caskets appear simple. Closer examination reveals an extraordinary degree of precision. The surfaces were carefully shaped and smoothed. The lids fit their bases with striking accuracy. Symmetry is maintained across multiple components. Internal cavities were hollowed with controlled dimensions while preserving structural integrity. Even more remarkable, these achievements were accomplished using technologies available nearly 2,000 years ago. To appreciate the challenge, it is useful to compare the relic caskets with other ancient precision stonework. Egyptian craftsmen produced finely finished granite sarcophagi. Roman artisans carved marble sculptures with astonishing detail. Indian stoneworkers created the polished pillars of Emperor Ashoka and the rock-cut architecture of Ajanta and Ellora. Yet each of these projects required highly specialized knowledge, sophisticated toolkits, and generations of accumulated expertise. The relic caskets of Lalitgiri belong within this broader tradition of precision craftsmanship, but their existence raises a difficult question. Why invest such extraordinary effort into objects that would remain hidden inside a sealed stupa? Microscopic examination suggests controlled shaping and finishing techniques that required exceptional skill. Stone is an unforgiving material. Remove too much and the piece is ruined. Apply uneven force and fractures can develop. Achieve symmetry on one surface but not another, and the final object becomes visibly imperfect. Modern machinists solve these problems with calibrated tools and measurement devices. Ancient artisans relied on experience, templates, abrasives, and techniques that remain poorly documented. The finished caskets demonstrate not only artistic ability, but also a practical understanding of geometry, material behavior, and manufacturing control. The nested arrangement of the containers introduces another layer of complexity. Multiple vessels were designed to fit within one another while maintaining dimensional compatibility. This implies planning before fabrication began. Each container had to be produced according to measurements that allowed the complete assembly to function as intended. Similar engineering logic appears in modern precision manufacturing, where components must meet predetermined tolerances. Whether ancient craftsmen thought in terms comparable to modern tolerances remains unknown, yet the physical evidence suggests they achieved remarkably accurate results. The mystery goes beyond craftsmanship. Creating these relic caskets required skilled artisans, training systems, workshops, tools, and resources. While the finished objects remain, the knowledge and infrastructure behind them disappeared centuries ago. The Bateshwar Temple Complex stands in the rugged sandstone hills of Morena district in Madhya Pradesh, India. More than 200 ancient Hindu temples are scattered across a remote valley that appears frozen in time. At first glance, the site seems like another forgotten archaeological ruin. Yet hidden among these weathered stones lies one of the most extraordinary engineering mysteries in Asia. Hundreds of temples collapsed during a devastating earthquake centuries ago, but remarkably, many of their structural components survived almost intact. Even more astonishing, modern archaeologists were able to reassemble large portions of the complex like a gigantic three-dimensional puzzle. The mystery is no longer who built Bateshwar. The mystery is how medieval engineers created a temple network capable of enduring forces that should have reduced it completely to rubble. The site became known to modern archaeology through surveys of central India conducted during the 20th century. Researchers eventually identified the remains as a vast temple complex dating primarily between the 8th and 10th centuries during the rule of the Gujara Pratihara dynasty. What they found challenged conventional assumptions about early medieval construction. Instead of a handful of isolated shrines, Bateshwar consisted of more than 200 temples arranged in clusters across the landscape. Many structures had collapsed, yet countless carved stones, pillars, roof sections and decorative elements remained remarkably well preserved. The deeper researchers investigated, the more they realized that Bateshwar represented not merely a religious center, but a sophisticated experiment in large-scale architectural engineering. The greatest mystery revolves around the earthquake that destroyed much of the complex. Geological evidence suggests that a significant seismic event struck the region centuries after construction. Under normal circumstances, a dense concentration of stone temples should have suffered catastrophic destruction. Stone structures are notoriously vulnerable to lateral seismic forces. Modern earthquakes have toppled masonry buildings throughout history, from parts of ancient Greece to medieval cities across the Middle East. Yet Bateshwar presents an unusual pattern. Many temples collapsed, but instead of disintegrating into unusable debris, large portions remained structurally recognizable. Columns survived, roof blocks survived, decorative carving survived. Entire architectural sections could still be identified after lying scattered for centuries. This raises an important engineering question. Did the builders unknowingly create a primitive form of seismic resilience? Archaeologists studying the site noticed that the temples were not built as monolithic masses. Instead, they consisted of numerous interlocking stone components assembled without large quantities of mortar. Many blocks were carefully shaped to distribute weight through gravity rather than chemical bonding. When seismic forces struck, the structures may have behaved differently from rigid masonry buildings. Instead of resisting movement until catastrophic failure occurred, parts of the temples could shift, separate, and collapse while preserving the integrity of individual components. This principle resembles certain earthquake-resistant concepts found in other ancient civilizations. Comparisons are frequently made with Inca stone architecture in Peru. At sites such as Machu Picchu, builders created walls using precisely fitted stones capable of absorbing seismic vibrations. Bateshwar does not employ the same polygonal masonry, yet both civilizations appear to have relied heavily on geometric stability and weight distribution rather than mortar strength. The comparison becomes even more intriguing when considering that the two societies were separated by thousands of kilometers and developed independently. Whether this similarity represents convergent engineering evolution or merely coincidence remains uncertain. Modern structural engineers have long recognized that flexibility often improves earthquake resistance. Japanese pagodas provide a famous example. Many survived centuries of earthquakes because their wooden cores allowed controlled movement. Bateshwar introduces a stone equivalent of this concept. Researchers have proposed that the modular nature of the temples may have reduced destructive stress concentrations. Instead of transmitting force through a single rigid frame, energy could dissipate through multiple joints and interfaces. While no medieval texts explicitly describe such an engineering strategy, the surviving evidence suggests that the builders understood structural behavior far better than traditionally assumed. Another mystery involves the astonishing standardization visible throughout the complex. More than 200 temples were constructed using remarkably consistent proportions. Pillars, platforms, roof components, and decorative elements follow recurring patterns with surprisingly small dimensional variations. Such consistency implies the existence of a sophisticated measurement system. Yet no surviving construction manuals explain how this standardization was achieved. Consider the challenge. Modern architects rely on detailed blueprints, standardized units, precision instruments, and quality control procedures. The builders of Bateshwar possessed none of these technologies in their modern form. Nevertheless, they produced hundreds of structures sharing common architectural language and geometric harmony. Researchers studying temple dimensions have observed recurring ratios that suggest careful planning rather than improvisation. Some scholars believe master builders employed standardized measuring rods or proportional design systems passed through generations of craftsmen. If so, much of that knowledge has disappeared. The transportation problem presents another unresolved puzzle. Every temple required enormous quantities of sandstone. Individual blocks often weighed several hundred kilograms, while larger architectural elements could exceed 1 ton. Today, cranes, trucks, and hydraulic equipment simplify such tasks. Medieval builders had access only to human labor, animals, and simple mechanical devices. Yet they successfully transported, shaped, and assembled enough material to create an entire sacred city. Comparisons with other ancient construction projects reveal the scale of the achievement. The temples are smaller than the massive monuments of Angkor Wat in Cambodia or Borobudur in Indonesia. However, Bateshwar compensates through density. More than 200 structures occupy a relatively compact area, creating logistical demands that remain poorly understood. Archaeologists still debate the exact organization of labor, the quarrying methods employed, and the transportation networks required to sustain construction over decades. Perhaps even more mysterious is the possibility that Bateshwar functioned as something larger than a religious complex. The remarkable repetition of architectural forms suggests a highly organized production system. Certain scholars have compared the site to a medieval architectural workshop operating on an unprecedented scale. Instead of constructing a single monumental temple, builders repeatedly refined and reproduced successful designs across hundreds of structures. This resembles a form of pre-industrial standardization rarely associated with the early medieval world. If this interpretation is correct, Bateshwar may preserve evidence of a sophisticated educational network. Teams of artisans likely shared templates, measurements, carving techniques, and structural knowledge. Master architects may have supervised entire generations of craftsmen. Such a system could explain the consistency observed throughout the complex, yet almost no written documentation survives to confirm how this knowledge was transmitted. The modern restoration of Bateshwar added a new chapter to the mystery. When archaeological teams began systematic reconstruction efforts, they encountered hundreds of thousands of scattered stones. At first, the task seemed impossible. Many temples had been reduced to enormous piles of architectural fragments accumulated over centuries. Yet as researchers carefully examined the pieces, patterns emerged. Individual blocks appeared designed to fit specific locations. Decorative sequences could be reconstructed, structural elements aligned with remarkable precision. The restoration was like solving a massive 3D puzzle without a reference image. Archaeologists relied on engineering logic, symmetry, and surviving fragments. Its success showed that the original designs were so consistent that experts could reconstruct parts of them even after more than 1,000 years. Mughalmari lies in the coastal plains of West Bengal, India. Beneath ordinary farmland near the town of Dantan, archaeologists uncovered the remains of a forgotten Buddhist center, whose engineering achievements continue to raise questions today. The modern rediscovery of Mughalmari was surprisingly recent. Although local villagers had long known about ancient bricks emerging from the ground after seasonal rains, systematic archaeological excavations only began in 2003. What researchers expected to find was a modest monastic complex dating to the early medieval period. What emerged instead was evidence of a large Buddhist institution that flourished between roughly the 6th and 12th centuries CE, during a time when Eastern India was one of the intellectual centres of the Buddhist world. Massive brick structures, elaborate terracotta decorations, monastic cells, courtyards, and religious architecture gradually appeared beneath centuries of accumulated soil. Yet the more archaeologists uncovered, the more difficult it became to explain how such a sophisticated complex could survive, function, and prosper in an environment that seems fundamentally hostile to long-term preservation. The first puzzle begins with the location itself. Mukalmari sits in a low-lying region influenced by monsoon rains, seasonal flooding, humidity, and fluctuating groundwater levels. Modern engineers recognize these conditions as particularly destructive for masonry architecture. Water infiltration weakens foundations, salts crystallize inside bricks, biological growth accelerates deterioration, and repeated wet-dry cycles gradually destroy structures. Yet substantial portions of Mukalmari survived for nearly a millennium after abandonment. This immediately raises questions about the knowledge possessed by its builders. Either they understood local geology and hydrology far better than previously assumed, or they employed construction techniques that have largely disappeared from the historical record. Excavations revealed extensive brick architecture characterized by remarkable consistency. Many ancient civilizations produced bricks, but Mukalmari's bricks demonstrate a level of standardization that suggests carefully controlled manufacturing processes. Archaeologists measured numerous bricks and found recurring dimensions throughout different sections of the complex. Standardization on this scale is not merely aesthetic, it reflects organization, quality control, and production systems capable of maintaining uniformity across thousands of construction elements. Similar patterns can be observed at Nalanda and other major Buddhist institutions of Eastern India. Yet the exact methods remain uncertain. Researchers can analyze surviving bricks chemically, but they still cannot fully reconstruct how ancient craftsmen consistently achieved such durable materials using technologies available more than 1,000 years ago. The durability itself presents another mystery. Modern fired bricks commonly experience significant deterioration within decades when exposed continuously to tropical environments without maintenance. Mukalmari's bricks endured centuries of monsoon conditions. Laboratory studies of ancient South Asian bricks often reveal firing temperatures between 700 and 1,000 degrees Celsius, depending on the clay composition and kiln design. Achieving and maintaining such temperatures consistently across large production batches would have required sophisticated control of fuel, airflow, and kiln structure. No surviving technical manuals describe these processes. The knowledge appears to have vanished while the products themselves remained. Yet perhaps the most astonishing discoveries at Mukalmari are neither its walls nor its foundations. They are the terracotta plaques that once decorated the monastery. These artifacts represent one of the most remarkable examples of artistic and technical craftsmanship in early medieval India, and they continue to challenge researchers attempting to understand how they were produced. At first glance, the plaques appear to be decorative elements depicting Buddhist figures, celestial beings, floral motifs, geometric patterns, animals, and scenes from religious traditions. Closer examination reveals something far more impressive. Individual details sometimes measure only a few millimeters across. Facial expressions remain recognizable. Jewelry patterns display extraordinary precision. Fabric folds, hair arrangements, and ornamental borders exhibit a complexity that rivals much later artistic traditions. Under magnification, many surfaces reveal astonishing levels of refinement despite being created from clay rather than stone or metal. The obvious question is how such consistency was achieved. If each plaque was sculpted entirely by hand, the labour investment would have been enormous. Hundreds of plaques have been recovered, many displaying remarkably similar proportions and stylistic characteristics. This has led some researchers to suggest the use of moulds or semi-standardized production techniques. However, the mystery does not end there. Even if moulds were used, the moulds themselves would have required master artisans capable of producing extraordinarily detailed prototypes. Furthermore, the firing process had to preserve delicate features without warping or cracking. Clay naturally shrinks during drying and firing. Maintaining geometric accuracy across large numbers of plaques would have required precise control over material composition and manufacturing procedures. Comparisons with other ancient civilizations make the achievement even more remarkable. Roman terracotta decorations often emphasized repetition and large-scale architectural ornamentation. Chinese ceramic traditions mastered high-temperature firing and detailed artistic production. Yet Mughalmari demonstrates a unique combination of religious symbolism, mass production, and miniature precision. Some decorative elements are so detailed that modern reproductions frequently require magnification tools and highly controlled workshop environments to achieve the comparable results. The ancient craftsmen accomplished this without modern measurement devices, electric kilns, or industrial manufacturing systems. The distribution of the plaques also raises questions about organization. Creating a few exceptional artworks is one thing. Producing hundreds of sophisticated decorative elements for a large architectural complex is another. Such output implies specialized workshops, trained artisans, supply chains for clay procurement, fuel acquisition, quality control, and possibly even apprenticeship systems. Very little direct evidence of these industrial processes survives. Archaeologists can observe the final products, but only partially reconstruct the organizational structures that made them possible. The mystery extends beyond art into information management. During its peak, Mughalmari was likely connected to major Buddhist networks stretching across eastern India and beyond. The monastery existed during a period when institutions such as Nalanda attracted students and scholars from multiple regions of Asia. Trade routes connected Bengal to Sri Lanka, Southeast Asia, and other parts of the Indian Ocean world. Such connections suggest that Mughalmari may have participated in extensive exchanges of ideas, texts, technologies, and religious practices. Yet almost none of the manuscripts that once existed have survived. Tropical climates are notoriously destructive to organic materials. Palm leaf manuscripts, wooden objects, textiles, and administrative records disappear rapidly without exceptional preservation conditions. What remains is architecture without its library, decoration without its documentation, and engineering without its instruction manuals. Water management presents another unresolved challenge. Any large monastic institution housing dozens or even hundreds of residents required reliable systems for drinking water, sanitation, drainage, and flood control. Modern archaeological surveys have identified certain structural features that may have played roles in water regulation, but a complete hydraulic picture remains elusive. This is surprising because long-term occupation would have been impossible without effective environmental management. The absence of clearly preserved infrastructure leaves researchers wondering whether major components remain buried beneath unexcavated areas, or whether perishable engineering solutions have vanished completely. Even the scale of Mughalmari remains uncertain. Only portions of the site have been excavated. Geophysical surveys and surrounding topography suggest that additional structures may still lie hidden underground. If future excavations reveal larger sections of the complex, current interpretations could change dramatically. Similar situations occurred at major archaeological sites across South Asia. where initial discoveries represented only a fraction of the original settlement. Every new trench at Mughal carries the possibility of uncovering evidence that reshapes our understanding of the monastery's size, function, and technological sophistication. Shijiahe culture was located within the floodplains of the middle Yangtze River in the present-day Hubei province, China. At first glance, the site appears to be another Neolithic settlement among the many cultures that emerged across ancient China. Yet beneath layers of earth lies evidence of a civilization that may have possessed engineering capabilities far beyond what archaeologists once believed possible for a society that existed more than 4,000 years ago. What makes Shijiahe remarkable is not simply its age. It is the growing realization that its builders created one of the largest urban centers in prehistoric East Asia, engineered sophisticated hydraulic systems, organized large-scale labor forces, and produced jade artifacts so precise that modern researchers still debate how they were manufactured without metal tools. The story began in the 1950s when archaeologists surveying the Jianghan Plain identified unusual concentrations of pottery and settlement remains. Subsequent excavations revealed that the area was not a village, but the center of a vast cultural complex covering hundreds of square kilometers. As excavation expanded, researchers discovered defensive walls, elite burials, workshops, ritual centers, reservoirs, canals, and an astonishing collection of jade artifacts. What initially appeared to be a regional farming society gradually transformed into one of the most important archaeological mysteries in China. The scale of Shijiahe immediately challenged traditional assumptions about Neolithic societies. The central settlement occupied roughly 8 to 12 square kilometers, making it one of the largest known urban centers in China around 2200 BCE. At a time when many contemporary communities consisted of small agricultural villages, Shijiahe supported a population that may have reached tens of thousands. Such a concentration of people required food production, water management, transportation systems, social organization, and administrative structures on a level rarely associated with Stone Age cultures. The first mystery emerges from the city's earthworks. Archaeologists identified enormous defensive embankments and engineered landscape modifications, constructed entirely without iron, bronze excavation machinery, wheeled transport, or draft animals comparable to those used in Mesopotamia. Millions of cubic meters of soil appear to have been moved and shaped. Even today, civil engineers recognize that earth-moving projects of this scale require extensive planning and labor coordination. Researchers can estimate the volume of material transported, but they still struggle to explain how such projects were organized with the technology available at the time. Comparisons are often made with the early cities of Mesopotamia, yet Shijiahe developed independently and under very different environmental conditions. The challenge became even greater when scientists examined the surrounding landscape. The Middle Yangtze Basin is prone to seasonal flooding, shifting waterways, and environmental instability. Building a major urban center in such an environment would have required advanced knowledge of hydrology. Satellite surveys, aerial mapping, and geological analysis have revealed evidence of canals, reservoirs, water control structures, and engineered drainage systems integrated into the wider landscape. These features suggest deliberate attempts to regulate water movement across a flood-prone region. Modern hydrologists studying the area have noted that many of the earthworks occupy positions that maximize flood protection while preserving access to agricultural land. The question remains how prehistoric engineers determined gradients, flow behavior, and long-term water management strategies without mathematical tools known from later civilizations. Yet the greatest mystery of Shijiahe is neither its walls nor its hydraulic engineering. It is jade. Thousands of jade artifacts have been recovered from elite burials and ritual contexts. To casual observers, they appear beautiful. Under scientific examination, they become deeply puzzling. Jade is one of the hardest materials worked by ancient humans. On the Mohs hardness scale, nephrite jade typically measures around 6 to 6.5, while many stone tools available to Neolithic craftsmen are significantly softer. Unlike wood or clay, jade cannot simply be carved. It must be slowly ground, drilled, polished, and shaped using abrasive materials over extended periods. Microscopic analysis of Shijiare jade artifacts has revealed astonishing precision. Researchers have identified grooves only fractions of a millimeter wide, perfectly symmetrical curves, highly polished surfaces, and complex geometric forms requiring exceptional control. Some objects contain internal perforations drilled through thick sections of jade while maintaining near-perfect alignment. Others display intricate relief carvings that would challenge even experienced artisans using modern hand tools. The conventional explanation proposes that craftsmen used quartz sand as an abrasive combined with cords, bamboo tools, stone drills, and immense patience. Experiments have demonstrated that such techniques can produce jade objects. However, replication studies often require extraordinary amounts of labor. Some modern experiments suggest that reproducing a single highly detailed jade artifact using only reconstructed Neolithic methods can require hundreds of hours of continuous work. When multiplied across thousands of artifacts discovered at Shijiahe, the scale of production becomes difficult to reconcile with traditional models. Even more puzzling is the consistency. Numerous jade objects display nearly identical dimensions and proportions. This suggests the existence of manufacturing standards, measurement systems, or production templates. Standardization on this level usually implies specialized workshops, skilled artisans, quality control procedures, and some form of technical knowledge transfer. Yet no written manuals survive. The knowledge system that supported this precision appears to have vanished completely. Several of the most famous Shijiayi jade artifacts possess unusual iconography unlike anything found elsewhere in China. Human-like faces with oversized eyes, abstract animal forms, hybrid creatures, and highly stylized masks dominate many ceremonial objects. Some scholars interpret these images as representations of deities or ancestral spirits. Others believe they formed part of a complex symbolic language connected to political authority. What remains unclear is why such a distinctive artistic tradition appeared at Shijiahe and then largely disappeared after the culture's decline. Recent scientific investigations have added another layer to the mystery. Geochemical studies indicate that some jade materials may have originated far from the settlement itself. If confirmed, this would imply long-distance trade networks extending hundreds of kilometers. Transporting raw jade across difficult terrain without wheeled vehicles would have required logistical systems of surprising sophistication. Similar long-distance exchange networks existed in contemporary civilizations, but the scale implied by the Shijiahi evidence suggests a level of regional integration that researchers are only beginning to understand. The mystery deepens further when examining the culture's final centuries. Around 2000 BCE, Shijiahi entered a period of rapid decline. Paleoclimate evidence points towards significant environmental changes affecting the Yangtze Basin. Sediment cores reveal indications of flooding events and climatic instability. Some researchers argue that catastrophic floods damaged agricultural production and forced population dispersal. Others propose social conflict, political fragmentation, resource shortages, or combinations of multiple factors. None of these explanations fully accounts for the abrupt disappearance of such a large and technologically capable center. Which mystery of Shijiahe fascinates you the most? Let us know your theory in the comments below. The Udayagiri Buddhist complex is hidden among the low hills of Odisha in eastern India. At first glance, it appears to be another forgotten Buddhist ruin. Yet beneath layers of earth that concealed it for centuries lies one of the most remarkable engineering puzzles in ancient South Asia. Archaeologists uncovered evidence of vast monasteries, sophisticated drainage systems, enormous stone sculptures, and construction techniques that continue to raise questions today. The mystery is not who built Udayagiri. Historians generally agree that the complex flourished between the 7th and 13th centuries CE under powerful Buddhist patronage. The real mystery is how ancient builders, working without modern surveying equipment, steel machinery, reinforced concrete, or written engineering manuals, created a massive hilltop complex whose technical achievements remain only partially understood. The modern rediscovery of Udayagiri occurred through archaeological investigations conducted during the 20th century, particularly large-scale excavations by the Archaeological Survey of India, beginning in the 1980s. What researchers initially expected to be a modest Buddhist site soon revealed itself as a sprawling monastic centre, covering multiple terraces across a hill landscape. Excavations uncovered large monasteries, shrines, stupas, sculptural workshops, residential areas, and hundreds of artifacts. As the layers of soil were removed, an unexpected picture emerged. Udayagiri was not simply a religious centre, it was an enormous engineering project. One of the first puzzles concerns planning. Modern engineers know that constructing large complexes on uneven terrain requires careful topographical analysis. Today, this would involve satellite mapping, digital elevation models, laser measurements, and structural calculations. Yet, the builders of Udayagiri transformed an irregular hill into a sequence of interconnected architectural platforms with astonishing precision. Large monasteries were positioned on leveled terraces while maintaining alignment with surrounding structures. Pathways, staircases, and ceremonial routes connected different elevations without disrupting the overall organization of the complex. Archaeologists have identified evidence that substantial portions of the hillside were reshaped before major construction began. This implies large-scale earth-moving operations whose logistics remain difficult to reconstruct. Unlike the Romans, who left extensive engineering texts, the builders of Udayagiri left virtually no technical documentation explaining how these calculations were performed. The challenge becomes even more impressive when considering climate. Odisha experiences intense monsoon rainfall. In some modern years, annual precipitation exceeds 1,500 millimeters. Water is one of the greatest enemies of ancient architecture, especially on slopes where runoff accelerates erosion. Yet many structures at Udayagiri survived for centuries before burial. Excavations revealed evidence of sophisticated drainage planning integrated directly into the architecture. Channels directed water away from foundations. Slopes appear to have been designed to control runoff. Retaining walls stabilized vulnerable sections of terrain. Modern geotechnical engineers understand that poor drainage can destroy even contemporary buildings. The fact that Udayagiri remained functional for hundreds of years suggests that its builders possessed practical hydrological knowledge far beyond what many assume for medieval South Asia. Perhaps the most intriguing mystery involves the bricks themselves. Throughout the site, archaeologists encountered bricks displaying remarkable durability, despite surviving centuries of monsoon exposure, temperature fluctuations, biological growth, and burial beneath heavy layers of sediment. Under normal conditions, ancient brick structures gradually deteriorate through cycles of moisture penetration, salt crystallization, thermal stress, and mechanical erosion. Yet many bricks recovered from Udayagiri retained sharp edges, structural integrity, and surprising uniformity. Their resilience has become one of the site's most fascinating engineering questions. Scientific analysis of ancient bricks elsewhere in India has demonstrated that durability depends on numerous variables, including clay composition, mineral content, firing temperature, kiln atmosphere, and manufacturing consistency. Even small differences can dramatically affect longevity. Modern industrial brick production relies on carefully controlled temperatures, often exceeding 900 to 1000 degrees Celsius. Achieving comparable consistency using ancient technologies would have required extraordinary expertise. Researchers suspect that Udayagiri's builders possessed highly refined knowledge of local clay sources and firing techniques. The uniformity observed in many surviving bricks suggests standardization rather than random production. Some scholars compare this achievement to the famous brick technologies of the Indus Valley Civilization, where standardized brick ratios were maintained across vast distances more than 2,000 years earlier. Yet, unlike modern factories, the workshops that supplied Udayagiri left behind few clues explaining how such consistency was achieved. The durability of these bricks becomes even more impressive when compared with other historical sites. Many medieval brick structures across tropical Asia have suffered severe deterioration due to moisture and vegetation. Portions of ancient monasteries at Nalanda required extensive conservation after centuries of exposure. Numerous brick monuments in Southeast Asia have undergone repeated restoration campaigns. Udayagiri's surviving materials demonstrate resistance that appears disproportionate to their age and environmental conditions. Scientists continue to investigate whether unique mineral compositions, specialized firing techniques, or construction methods contributed to this longevity. No definitive explanation has yet emerged. Another mystery surrounds transportation. The site contains large stone sculptures, architectural blocks, decorative elements, and massive carved images of the Buddha and Bodhisattvas. Some individual pieces weigh several tons. Transporting such materials across uneven terrain remains difficult even today. Modern construction projects rely on cranes, trucks, hydraulic systems, and engineered roads. Medieval builders possessed none of these advantages. Archaeologists believe workers likely used combinations of earthen ramps, rollers, ropes, wooden sledges, and coordinated labor forces. However, direct evidence remains scarce. Similar questions surround the construction of Borobudur in Indonesia, Angkor in Cambodia, and Machu Picchu in Peru. In each case, researchers understand the final result but continue debating the precise logistical methods that made it possible. The sculptural program of Udayagiri introduces another technical puzzle. The site contains some of the finest Buddhist carvings in eastern India. Many statues exhibit remarkable proportional consistency, despite being produced across different periods. Facial dimensions, body ratios, ornamental details, and symbolic features often follow strict patterns. This suggests the existence of standardized design systems. Ancient craftsmen may have used geometric grids, measurement canons, or mathematical formulas similar to those employed in classical Greek sculpture and traditional Indian architectural treatises. Yet, the practical methods used to transfer these designs from concept to finished monument remain uncertain. The precision achieved by artisans working with simple tools continues to impress modern researchers. Researchers have also explored possible astronomical considerations in the site's layout. While evidence remains debated, certain architectural alignments appear too deliberate to dismiss entirely. Across the ancient world, Major ceremonial centres often incorporated astronomical observations into their design. Examples include Stonehenge in Britain, Chichen Itza in Mexico, and Angkor Wat in Cambodia. Whether Udayagiri participated in a similar tradition remains unresolved. Nevertheless, the possibility suggests a level of planning that extended beyond architecture into environmental observation and celestial knowledge. Located on the edge of the Abalessa oasis in southern Algeria, deep within the central Sahara near the Hoggar Mountains, the tomb of Tin Hinan remains one of North Africa's most intriguing archaeological mysteries. In 1925, a French archaeological expedition opened the massive stone mausoleum traditionally linked to Tin Hinan, the legendary ancestral queen of the Tuareg people. Inside, researchers uncovered the remains of a woman buried with gold jewellery, silver ornaments, glass objects, and artefacts connected to the Roman world. The discovery immediately sparked questions that remain unresolved nearly a century later. The mystery extends beyond the identity of Tin Hinan herself. More puzzling is how such a sophisticated stone monument could have been designed, supplied, and constructed in one of the most unforgiving environments on Earth. Modern archaeology can measure the tomb, analyze its materials, and date many of its contents. Yet it still struggles to explain the engineering systems, logistical networks, and technical knowledge that made the monument possible. The mausoleum itself is an architectural anomaly. Built from carefully arranged stone blocks, the structure contains multiple chambers connected through a planned internal layout. Archaeological surveys have documented 11 separate rooms, organised within a rectangular complex measuring roughly 26 metres in length. While this size may seem modest compared with the pyramids of Egypt or the imperial tombs of China, the challenge lies in its location rather than its dimensions. The Sahara is not simply a desert, it is the largest hot desert on Earth, covering approximately 9 million square kilometres. Summer temperatures frequently exceed 45 degrees Celsius. Annual rainfall can fall below 50 millimetres in many regions, and water sources are often separated by hundreds of kilometres. Every stone transported, every worker fed, and every construction activity organised required logistical solutions that remain largely invisible in the archaeological record. One of the first mysteries concerns the sourcing and movement of construction materials. Researchers have identified local stone sources around the Hoggar region, but identifying a quarry is only the beginning of the problem. The builder still needed to extract, shape, transport, and precisely position large quantities of stone without wheeled transport systems, comparable to those used in later civilizations. Similar questions have been raised at sites such as Stonehenge in Britain, where some stones travelled over 200 kilometres, and at the Yangshan quarry in China, where unfinished megaliths demonstrate the enormous difficulty of moving massive stone blocks. Tin Hinan's builders faced an additional obstacle: desert terrain. Sand dramatically increases friction, reducing transport efficiency. Even modern military logistics treat desert operations as exceptionally difficult. Yet ancient builders succeeded in creating a durable monument that survived for more than 16 centuries. The geometric organization of the tomb presents another puzzle. Archaeologists have noted that the chambers follow a coherent architectural plan rather than an organic accumulation of rooms. This implies surveying methods capable of maintaining alignment, spacing, and structural stability. Modern surveyors rely on optical instruments, laser measurements, satellite positioning, and digital modelling. Ancient builders possessed none of these tools. Nevertheless, they achieved results that suggest careful measurement and planning. Similar questions arise at Roman military camps, Egyptian temples, and Inca settlements. Across the ancient world, accurate geometry repeatedly appears long before the invention of modern engineering mathematics. Tin Hinan tomb belongs to this broader pattern, yet the exact techniques used by its builders remain unknown. The burial chamber itself introduces one of the most debated technical mysteries. The woman's remains were discovered in a remarkably preserved state considering the age of the tomb. Sahara conditions undoubtedly contributed to preservation, but environmental factors alone may not fully explain the phenomenon. The internal design of the structure appears to have created a stable microclimate. Temperature fluctuations, airflow, humidity levels, and chamber orientation all influence preservation rates. Today, museums spend millions of dollars controlling these variables through climate-controlled systems. The possibility that ancient builders unintentionally or deliberately created similar environmental stability raises intriguing questions about empirical knowledge accumulated through generations of observation. The artifacts found within the tomb reveal an even larger mystery extending far beyond the structure itself. Archaeologists recovered gold bracelets, silver jewellery, glass objects, and a Roman coin believed to date to the reign of Emperor Constantine during the 4th century CE. Such discoveries demonstrate that Abalessa was connected to networks extending across thousands of kilometers. Trade routes linked North Africa, the Mediterranean coast, the Sahara, and sub-Saharan Africa long before modern roads existed. Maintaining these routes required sophisticated navigation, resource management, and communication systems. A caravan crossing the Sahara often traveled hundreds or even thousands of kilometers between major population centers. Water availability determined survival. A single navigational error could prove fatal. Yet trade flourished for centuries. The existence of imported luxury goods in Tin Hinan's tomb indicates that these logistical systems operated with remarkable efficiency. Some historians compare Sahara trade networks to maritime shipping lanes. Both required detailed environmental knowledge, reliable routes, predictable stopping points, and organizational structures capable of coordinating long-distance movement. The difference is that sailors navigated oceans, while Saharan traders crossed landscapes that often appeared featureless. Modern satellite imagery reveals ancient caravan routes threading across the desert like invisible highways. Many were established centuries before Tin Hinan's lifetime. The engineering challenge was not constructing roads, but maintaining navigational knowledge across generations. How this information was preserved remains only partially understood. Debate also surrounds the age of the monument itself. Most researchers place the burial in the 4th or 5th century CE based on associated artifacts. However, some scholars have suggested that the structure may have undergone multiple phases of use. Architectural modifications visible in certain sections hint at possible additions or renovations. Similar patterns appear at royal tombs throughout the ancient world. Egyptian pyramids often incorporated earlier structures. Roman buildings frequently reused older foundations. In the Andes, successive cultures repeatedly rebuilt ceremonial centers over existing sacred locations. If Tin Hinan tomb followed a comparable pattern, parts of the structure could potentially be older than the burial itself. Evidence remains inconclusive, but the possibility continues to attract scholarly interest. The identity of Tin Hinan presents another layer of uncertainty. Tuareg oral traditions describe her as a founding queen who migrated into the Ahaga region and became the ancestral mother of important Tuareg lineages. Oral traditions can preserve historical information across surprisingly long periods. Modern research into Polynesian navigation, indigenous Australian traditions, and African oral histories has demonstrated that some narratives retain accurate memories for centuries. Yet separating historical fact from symbolic mythology remains difficult. Genetic studies conducted on the remains have generated additional debate regarding ancestry and population movements in the Sahara. Instead of resolving the mystery, scientific analysis has often complicated it by revealing evidence of cultural interactions across vast regions. Dir Kathar lies in the forested hills of Madhya Pradesh in central India. Scattered across a quiet landscape are the remains of more than 30 ancient Buddhist stupas dating back over 2,000 years. At first glance, the site appears modest compared to famous monuments such as Sanchi. Yet the deeper archaeologists investigated Dir Kathar, the more they encountered a mystery hidden not in legends or lost treasures, but in engineering. How did builders working during the Mauryan and post-Mauryan periods create monuments capable of surviving more than 20 centuries of monsoon rains, temperature fluctuations, biological erosion, and human activity? Even more puzzling, how did they accomplish this without modern surveying equipment, structural analysis, cement, steel reinforcement, or written engineering manuals? The modern rediscovery of Dir Kathar occurred relatively recently. Archaeological surveys conducted in the late 20th century revealed an extensive Buddhist complex spread across a remote region of central India. Excavations uncovered stupas, monastic remains, stone railings, inscriptions, and fragments of pillars associated with the era of Emperor Ashoka. What initially appeared to be an isolated religious centre soon emerged as one of the most important archaeological windows into the early expansion of Buddhism across the Indian subcontinent. Yet every excavation seemed to raise more questions than answers. One of the first mysteries involves the remarkable level of planning visible across the landscape. The stupas were not randomly scattered. Their placement suggests deliberate spatial organization that integrated terrain, visibility, movement, and ceremonial function. Modern survey measurements indicate that several structures occupy positions that maximize sightlines across the surrounding hills. Such planning may sound simple today, but achieving it over uneven terrain without modern instruments required sophisticated practical knowledge. Ancient builders had to measure distances, establish alignments, maintain proportional relationships, and account for natural topography. Similar planning principles can be observed at Sanchi, nearly 200 kilometers away, yet the exact methods used by ancient surveyors remain largely unknown. The stone components discovered at the site introduce another layer of mystery. Archaeologists identified fragments believed to be associated with Ashokan pillars. These pillars belong to one of the most technically impressive stoneworking traditions of the ancient world. Some surviving Ashokan pillars elsewhere in India stand more than 12 meters tall and weigh between 30 and 50 tons. Their surfaces display the famous Mauryan polish, a finish so smooth that it reflects light almost like modern polished stone. Researchers have attempted to reproduce this finish experimentally using traditional abrasives, yet no consensus exists regarding the precise combination of materials and techniques that created such extraordinary results. Under microscopic examination, some Mauryan surfaces exhibit a consistency that continues to challenge explanations based solely on simple hand polishing. Transportation presents an equally difficult puzzle. Large stone elements associated with Mauryan construction were often quarried dozens or even hundreds of kilometers from their final destinations. Moving a 40-ton monolithic pillar without steel cranes, modern roads, hydraulic systems, or mechanized transport would have required logistical capabilities on an enormous scale. Historians propose combinations of wooden rollers, sledges, labour teams and river transport, but direct archaeological evidence remains scarce. Every surviving pillar raises the same question. How did ancient engineers repeatedly transport and erect structures weighing as much as modern military vehicles while maintaining such precision? Yet the greatest mystery of Dur Cathar may be found within the stupas themselves. Most ancient structures constructed primarily from earth and brick have long since vanished. Wind, rain, vegetation, earthquakes, and human activity gradually destroy even substantial monuments. Dur Cathar presents a different story. Despite more than 2,000 years of exposure, significant portions of multiple stupas remain recognizable today. This survival becomes even more remarkable when compared with the environmental conditions of central India. The region experiences annual monsoon cycles, capable of delivering substantial seasonal rainfall. Water is among the most destructive forces affecting archaeological structures. Once moisture penetrates a monument, repeated expansion, contraction, biological growth, and erosion can rapidly weaken the entire system. Modern conservation projects often struggle to protect masonry structures that are only a few centuries old. Yet Dur Cathar's builders created monuments that resisted environmental degradation for over 20 centuries. Archaeological studies suggest that this longevity was not accidental. Examination of surviving structures indicates the use of layered construction techniques. Rather than relying on a single material, builders combined compacted earth, stone fragments, brick components, and exterior protective layers into integrated systems. Modern engineers would describe such an approach as a composite structure. Each layer performs a different function. Dense inner cores provide stability. Intermediate materials absorb stresses. Exterior surfaces reduce weathering. Together they create a monument more resilient than any single material could achieve independently. What makes this particularly intriguing is that similar principles appear in modern geotechnical engineering. Contemporary embankments, dams, and earth-retaining structures often employ multiple layers designed to distribute stress and manage water infiltration. The builders of Dur Cathar appear to have reached comparable solutions through empirical observation more than 2 millennia earlier. The challenge is that no surviving manuals explain how they developed this knowledge. The mystery deepens when researchers analyze structural geometry. Stupas typically feature hemispherical or dome-like forms. Modern structural analysis demonstrates that curved geometries distribute loads efficiently by directing forces downward and outward. This reduces stress concentrations that might otherwise cause cracking or collapse. The same principle explains why arches and domes became fundamental elements of Roman engineering centuries later. Yet many early Indian stupas predate some of the most famous Roman examples. Were ancient builders consciously applying structural principles, or did generations of experimentation gradually refine designs toward optimal forms? The evidence remains inconclusive. Water management may hold another key to the extraordinary lifespan of the monuments. Even small failures in drainage can dramatically shorten the life expectancy of earthen structures. Surveys around Dur Cathar suggest that builders paid careful attention to terrain gradients and runoff patterns. Many stupas occupy slightly elevated positions where water naturally drains away from foundations. This seemingly simple decision may have increased structural longevity by centuries. Modern archaeological mapping increasingly reveals that ancient builders possessed a sophisticated understanding of hydrology despite lacking formal scientific terminology. Another unresolved question is maintenance. Ancient communities likely repaired damage and reinforced weak areas over time, but the exact methods used at Dur Cathar remain unknown. The site's survival may be due to both long-term care and exceptionally durable original construction, making it difficult for archaeologists to determine which factor mattered most. What do you think explains the extraordinary survival of the Dur Kothar stupas for more than 2,000 years? Was it advanced engineering knowledge, centuries of maintenance, or a combination of both? Share your thoughts in the comments below. In present-day Chhattisgarh in central India lies Ranthambore, once the capital of the powerful Kalachuri dynasty. Today it is a quiet town surrounded by forests, lakes and temple ruins. Archaeologists have known about the site for centuries, but systematic studies during the colonial period and later surveys by the Archaeological Survey of India revealed something far more intriguing than a forgotten medieval capital. Beneath the surviving temples, collapsed walls, reservoirs and scattered stone blocks lies evidence of an engineering tradition whose full sophistication remains only partially understood. Historians can identify the rulers who governed Ranthambore. They can estimate construction dates and reconstruct political events. Yet many of the technologies that allowed builders to create and maintain this urban centre for hundreds of years remain difficult to explain. The mystery is not who built Ranthambore. The mystery is how medieval engineers working without modern surveying instruments, reinforced concrete, steel machinery, or written engineering manuals achieved such remarkable results. The first clue appears in the city's overall layout. Ranthambore was not constructed randomly. Archaeological mapping reveals a carefully organised settlement centred around religious monuments, defensive structures, artificial water bodies, and transportation routes. The arrangement suggests advanced planning extending across several square kilometres. Such planning required accurate measurements, labour coordination, and long-term resource management. Similar organisational complexity is often associated with major centres such as Angkor in Cambodia or the Chola capitals of southern India. Yet Ranthambore remains far less studied despite displaying many of the same characteristics. Among the most impressive surviving structures is the Mahamaya Temple, one of the oldest and most significant monuments in the region. Built primarily from stone blocks, the temple demonstrates an extraordinary understanding of structural balance. Modern engineers examining ancient Indian temples frequently note that many survived earthquakes, monsoon cycles, and centuries of weathering despite lacking steel reinforcement. Ranthambore presents the same puzzle. The temple's weight is distributed through a system of load-bearing walls, interlocking stone components, and carefully calculated proportions. The builders possessed no computer models, yet the structure has remained standing for nearly 1,000 years. Researchers can measure the geometry, but the precise methods used to calculate stability remain uncertain. The mystery deepens when examining the stone itself. Some of the blocks display carving precision measured in millimeters. Decorative patterns remain visible despite centuries of exposure to rain, humidity, biological growth, and temperature fluctuations. Geological studies suggest that builders deliberately selected stone varieties capable of resisting weathering. This implies practical material science knowledge developed through generations of experimentation. The challenge is that almost none of the technical knowledge survived in written form. The monuments remain, but the engineering principles behind material selection largely disappeared. Water management may represent the greatest technological achievement of ancient Ranthambore. Central India experiences dramatic seasonal variations. During monsoon months, rainfall can be intense. During dry periods, water becomes far more limited. Sustaining a large urban population under such conditions required sophisticated hydraulic engineering. Archaeologists have identified reservoirs, tanks, channels, and interconnected water storage systems throughout the region. Some reservoirs remain functional even today. What makes these systems remarkable is their apparent ability to regulate water flow naturally. Engineers had to calculate gradients carefully enough to move water efficiently while preventing erosion. A slope that is too steep accelerates destructive flow. A slope that is too shallow prevents circulation. Modern hydraulic engineers solve such problems using precise calculations and surveying equipment. Medieval builders at Ratanpur achieved similar outcomes using technologies that remain poorly documented. Comparisons with other hydraulic civilizations highlight the significance of this accomplishment. The Roman aqueducts transported water across hundreds of kilometers, with gradients often measured in centimeters per kilometer. Angkor's reservoirs transformed Cambodia's landscape through massive water control projects. The Hohokam culture in North America built hundreds of kilometers of irrigation canals. Ratanpur operated on a smaller scale, yet the same engineering principles appear evident. The unresolved question is how knowledge of terrain analysis and water behavior was transmitted across generations without surviving technical manuals. The transportation of construction materials introduces another mystery. Many stone blocks used in temples and fortifications weigh several tons. Moving such material requires substantial logistical planning. Even modern construction projects rely on cranes, vehicles, and specialized equipment. Medieval builders depended primarily on human labor, animals, ropes, ramps, and mechanical advantage. Historians can propose theoretical methods, but direct evidence remains limited. No detailed engineering records explain how the larger stones reach their final positions. Experimental archaeology offers clues. Reconstructions suggest that teams using wooden rollers, earthen ramps, and coordinated pulling systems can move surprisingly heavy loads. Similar methods have been demonstrated for Egyptian pyramids, Roman monuments, and Inca architecture. Yet each environment presents unique challenges. The terrain surrounding Ratanpur includes seasonal wetlands, uneven ground, and dense vegetation. Moving large stones across such landscapes would have required extraordinary organization. The exact techniques remain uncertain. The defensive architecture of Ratanpur presents another puzzle. Historical accounts describe the city as a major political center protected by fortifications. Portions of these defensive systems survive today. Archaeologists believe the city's designers integrated walls, gates, water bodies, and natural topography into a unified defense network. Such integration required strategic planning extending beyond individual buildings. Comparable military engineering can be observed at forts such as Daulatabad in Maharashtra or Chittorgarh in Rajasthan. Yet many details of Ratanpur's original defensive system have vanished, making reconstruction difficult. One particularly intriguing aspect is the relationship between hydraulic infrastructure and defense. Several reservoirs may have served dual functions. During peaceful periods, they provided water storage. During conflict, they potentially acted as obstacles slowing attackers. This combination of civil and military engineering demonstrates a level of systems thinking often underestimated in discussions of medieval technology. Astronomical alignment may also have played a role in the city's design. Many Indian temples incorporate orientations linked to solar events, cardinal directions, or ritual calendars. Preliminary studies suggest certain structures at Ratanpur follow deliberate alignments rather than random positioning. Similar patterns occur at Konark, Khajuraho, and numerous sacred sites throughout South Asia. Whether these alignments served symbolic, practical, or astronomical functions remains debated. What is clear is that achieving consistent orientations across multiple structures required reliable surveying methods. The greatest mystery of Ratanpur may be the invisible technological ecosystem that supported construction itself. Every monument implies the existence of quarry workers, surveyors, stonemasons, transport specialists, hydraulic engineers, architects, and administrators. These specialists required training systems capable of preserving technical knowledge over generations. Yet the workshops where that knowledge was taught have largely disappeared. The tools have vanished. The instruction methods are unknown. Only the finished products remain. The dry hills of southeastern Attica in mines of Lorien conceal a labyrinth so vast that modern archaeologists still cannot map all of it. More than 2,000 vertical shafts descend into the rock. Hundreds of kilometers of tunnels twist through the earth beneath Greece. Some are barely wide enough for a human body to crawl through. Yet over 2,000 years ago, these mines produced enough silver to transform Athens into the dominant power of the ancient Mediterranean. The deeper researchers study Lorien, the stranger it becomes, because this was not simply a primitive mine. In many ways, it functioned like an industrial complex operating centuries before the industrial age supposedly began. The mines were known in Iranian antiquity, but their true scale only became clear during the 19th century when modern mining companies reopened parts of the ancient workings. Archaeologists soon discovered enormous underground networks, washing facilities, furnaces, drainage systems, and ventilation shafts preserved beneath the landscape. Later geological surveys revealed that ancient miners had followed narrow silver-bearing galena veins with astonishing precision, often deep underground and across multiple levels. The first mystery is scale. Modern estimates suggest the Lorien mining district contained more than 5,000 individual mining works, approximately 2,000 shafts, hundreds of kilometers of tunnels, and extraction depths exceeding 100 meters. For comparison, many European medieval mines remained far smaller and less organized more than 1,000 years later. What shocks engineers today is not only the quantity of excavation, but the accuracy of it. The silver-bearing mineral at Lorien mainly existed in thin galena veins trapped within limestone formations. Missing the vein by even a few meters could mean excavating useless rock for weeks. Yet ancient miners repeatedly tracked these veins with extraordinary efficiency, despite having no seismic imaging, no geological maps, no explosives, no electric lighting, and no precision drilling tools. Even so, many tunnels curve almost perfectly alongside ore deposits, adapting to changes in rock direction in ways remarkably similar to modern mining logic. Some shafts intersect other tunnels with surprising precision, despite being dug from different underground levels. Researchers still debate how ancient surveyors maintained orientation inside total darkness, with only oil lamps and hand tools. Experimental archaeologists estimate that removing a single cubic meter of hard limestone using iron chisels and hammers could require dozens of labor hours. At Lorien, millions of cubic meters were excavated. This raises a disturbing possibility. The organizational and geological knowledge of the ancient Greeks may have been far more advanced than traditionally assumed. Air was one of the deadliest problems in ancient mining. Deep underground tunnels accumulate carbon dioxide, heat, toxic dust, lead particles, and smoke from oil lamps. Even in 18th century Europe, poor ventilation killed miners regularly, yet Lorien operated continuously for centuries. Archaeologists discovered that many vertical shafts in the mines were not designed primarily for extraction. Instead, they appear positioned specifically to create airflow circulation. Some tunnels were constructed at carefully chosen gradients, while others connected multiple underground levels in ways that naturally pulled warm air upward while drawing cooler air downward. Modern airflow simulations suggest several shafts were placed in near-optimal positions for passive ventilation. This is difficult to explain through simple trial and error, because moving a shaft even slightly can drastically reduce airflow efficiency underground. Yet many Lorien passages appear deliberately engineered around air movement. Ancient Greek writers never left a complete technical explanation of these systems, and that missing knowledge has become one of the site's greatest mysteries. Did miners slowly develop empirical airflow science through generations of experimentation, or did a larger body of mining engineering knowledge disappear completely from history? The region around Lorien is dry and harsh. Annual rainfall is low, and water shortages have existed there since antiquity. That makes the next discovery even more confusing. Researchers uncovered massive ore washing complexes throughout the mining district containing sedimentation tanks, stone channels, crushing floors, filtration basins, and water recycling systems. These facilities were designed to separate silver-bearing minerals from waste rock through density differences. Crushed ore was washed repeatedly so heavier galena particles settled while lighter material was removed. But the process required enormous quantities of water. To solve this problem, the ancient Greeks built highly sophisticated hydraulic systems, including large cisterns carved into rock, rainwater collection networks, settling basins, and closed-loop recycling channels. Some waterproof coatings inside the cisterns still function after more than 2,000 years. The industrial scale is staggering. At several processing sites, archaeologists estimate thousands of tons of ore could be treated annually. Entire landscapes around Lorien were transformed into interconnected mining and refining zones. This does not resemble isolated ancient workshops. It resembles an organized industrial economy operating in the classical world centuries before industrialization supposedly began. The most difficult technological mystery at Lorien begins after extraction. Silver in the mines mostly existed within galena ore, a lead sulfide mineral containing only small amounts of precious metal. To obtain silver, ancient metallurgists had to perform a dangerous and extremely delicate process known as cupellation. This required crushing the ore, smelting lead from sulfur compounds, reheating the lead inside oxygen-rich furnaces, and separating silver from oxidized lead. The process sounds simple in theory, but in reality it is extraordinarily difficult. Silver melts at approximately 962 degrees Celsius, while lead melts at only 327 degrees Celsius, and lead oxide formation depends heavily on oxygen concentration and furnace temperature. If temperatures were too low, separation failed entirely. If temperatures became too high, silver losses increased dramatically, furnaces destabilized, and fuel consumption exploded. Modern metallurgists examining Lorien slag discovered something astonishing. The remaining silver content inside ancient waste material is often surprisingly low. In some samples, extraction efficiency appears far beyond what historians expected from classical age technology. This means Lorien workers were controlling furnace environments with exceptional precision despite lacking thermometers, modern chemistry, steel temperature probes, or industrial bellows systems. Even more mysterious is the consistency. Some furnace remains indicate relatively stable heating conditions across repeated smelting cycles. Maintaining such control using charcoal fires alone would require remarkable expertise. Researchers believe Lorien metallurgists may have relied on highly refined observational methods involving flame color, sound resonance, airflow behavior, smoke density, and subtle color changes in molten lead. Essentially, they may have developed a practical thermal science entirely through experience. Experimental archaeology projects attempting to recreate ancient Greek cupellation found that even small changes in airflow could alter silver yield dramatically. In several modern reconstructions, maintaining stable furnace conditions for long periods proved extremely difficult even for trained teams with modern understanding of metallurgy. And yet, Lorien achieved production on an enormous scale. This has led some historians to argue that ancient metallurgical knowledge may have been far more sophisticated than surviving texts suggest. Because what existed at Lorien was not crude metalworking, it was precision industrial chemistry without modern scientific language. One of the most shocking discoveries connected to Lorien did not happen in Greece, it happened in Greenland. Ice core studies revealed spikes in atmospheric lead pollution dating back more than 2,000 years. Isotopic analysis linked much of that pollution directly to Mediterranean silver production, including Lorien. This means the mines produce contamination on a hemispheric scale. Ancient Athens was releasing enough lead into the atmosphere for traces to travel thousands of kilometers and become trapped in Arctic ice. Pollution levels rose during periods of intense Athenian expansion and dropped sharply during wars and economic collapse. The implication is extraordinary. Lorien may represent one of humanity's earliest examples of industrial-scale environmental impact. Long before factories, steam engines, or modern capitalism, an ancient civilization had already created pollution detectable across the planet. Do you think the ancient Greeks possessed technological knowledge far beyond what history officially recognizes? Share your thoughts in the comments below. Watek Phnom rises from the flat floodplains of northwestern Cambodia, like the remains of a civilization that understood engineering far beyond what historians once believed possible. Archaeologists first documented the temple during French colonial surveys in the late 19th century, but its true complexity only became clear after structural and geological studies revealed something strange. This massive stone monument had survived nearly 1,000 years on unstable tropical soil that should have caused catastrophic collapse centuries ago. Built during the 11th century under the Khmer Empire, Watek Phnom is often overshadowed by Angkor Wat, yet many researchers now believe it may preserve clues about forgotten construction techniques, material science, and environmental engineering that remain only partially understood today. The first mystery begins beneath the temple itself. Battambang sits in a region heavily affected by seasonal flooding, groundwater movement, and soft alluvial sediments. Modern engineers know that constructing multi-thousand-ton stone structures on such terrain is extremely dangerous without deep foundations or reinforced stabilization systems. Yet Watek Phnom has remained standing for almost a millennium despite earthquakes, monsoon cycles, root intrusion and soil movement. Excavations reveal that Khmer builders created layered laterite platforms beneath the temple, possibly designed to distribute weight across unstable ground. Laterite, an iron-rich tropical soil that hardens when exposed to air, acted almost like a primitive concrete. What shocked researchers was the density and compression of these layers. In some areas, the laterite foundation reached compressive strengths, approaching low-grade modern masonry materials after centuries of natural mineralization. The engineering becomes even more puzzling when compared to other ancient civilizations. Roman builders relied on pozzolanic volcanic concrete capable of resisting seawater for over 2,000 years. The Egyptians built pyramids on stable limestone plateaus to minimize subsidence. But Khmer architects faced one of the worst possible environments for long-term stone construction. Tropical wetlands with intense rainfall exceeding 1,300 millimeters annually. Despite this, the temple's central sanctuary remains relatively aligned. Some structural surveys suggest deviations smaller than a few centimeters across sections several meters wide. An astonishing level of stability for a medieval Southeast Asian construction. The stones themselves present another unresolved mystery. Many of the sandstone blocks appear tightly fitted with minimal mortar. Some joints are so narrow that even thin blades struggle to pass between them. Historians traditionally argue that Khmer workers used iron chisels, wooden levers, and manual polishing techniques. But microscopic analysis of certain tool marks suggests repetitive abrasion patterns more consistent with advanced sanding processes than crude hammering alone. Researchers believe quartz sand mixed with water may have been used as an abrasive cutting compound, similar to techniques proposed for ancient Egyptian granite work. However, recreating the same precision using replicated medieval Khmer tools has proven extremely difficult. Even more mysterious is the transportation problem. Some sandstone blocks used at Wat Ek Phnom weigh several tons and likely originated from quarries located dozens of kilometers away. Moving such stones through floodplains and jungle terrain without wheeled heavy machinery would have required enormous coordination. Scholars estimate that transporting a single large block could have demanded hundreds of labourers using wooden sledges, bamboo rollers, and seasonal waterways. Yet, no surviving Khmer texts explain the logistical systems behind these operations. This absence of documentation has fueled speculation that the Khmer Empire possessed organizational and engineering capabilities far more advanced than traditionally assumed. The carvings at Wat Ek Phnom deepen the mystery further. Many pediments and lintels display highly symmetrical geometric patterns and mythological scenes carved with remarkable consistency. Some decorative grooves are only millimeters deep, yet maintain clean proportions after nearly 1,000 years of erosion. Sandstone is softer than granite, but it fractures easily under uncontrolled pressure. Achieving such detail repeatedly would have required extraordinary control over carving angles and force distribution. Certain historians believe Khmer artisans may have employed proportional measurement systems or reusable geometric templates. If true, this would suggest standardized architectural mathematics operating across multiple Khmer temple sites centuries before modern surveying instruments existed in the region. The climate resistance of the structure is equally difficult to explain. Cambodia's environment is among the harshest in Southeast Asia for preserving exposed stone architecture. High humidity accelerates biological growth, while thermal expansion and acidic rainfall gradually fracture mineral surfaces. Yet many laterite sections at Wat Ek Phnom remain surprisingly durable. Scientific studies on laterite used in Khmer construction found that oxidation of iron compounds over time may create hardened outer shells that naturally protect interior material from rapid decay. In other words, parts of the temple may have slowly strengthened themselves through long-term chemical transformation. This phenomenon has drawn comparisons to Roman marine concrete, which becomes stronger through interaction with seawater crystals over centuries. In both cases, ancient builders may have unintentionally exploited chemical processes modern science only recently began fully understanding. The difference is that Roman engineering texts survived. Khmer engineering methods largely disappeared with the decline of the empire, leaving modern researchers to reconstruct fragmented clues from ruins alone. Another unresolved question involves astronomical alignment. Like many Khmer temples, Wat Ek Phnom appears carefully oriented along cardinal directions. Certain corridors and gateways align closely with solar movement during specific times of the year. Achieving this level of orientation without magnetic compasses or optical instruments would have required repeated long-term sky observations. Researchers studying Khmer architecture found that many temples across Cambodia share remarkably consistent directional patterns over distances spanning hundreds of kilometers. This suggests the existence of a standardized cosmological or astronomical surveying system. Some scholars propose that Khmer architects track solar shadows using fixed observation poles and seasonal horizon markers. Others argue that water reflection techniques may have helped establish visual alignment baselines, but no surviving evidence fully explains how large-scale directional accuracy was maintained across generations. The mystery becomes even greater when considering the immense labor coordination required to keep temples aligned despite uneven terrain and shifting foundations. Hydraulic engineering may hold another hidden clue. The Khmer Empire is famous for massive reservoirs and canal systems surrounding Angkor, but smaller regional temples like Wat Ek Phnom were also integrated into sophisticated water management networks. Satellite imaging and ground surveys have identified ancient moats, embankments, and channels surrounding the temple complex. These systems likely served religious symbolism, irrigation control, and flood management simultaneously. Some archaeologists believe Khmer hydraulic infrastructure was so advanced that it allowed dense urban populations to survive seasonal climate extremes for centuries. Yet this same system may have contributed to collapse. Paleoclimate studies indicate Southeast Asia experienced severe megadroughts between the 14th and 15th centuries. Tree ring data and sediment analysis suggest alternating cycles of devastating droughts and extreme monsoon flooding destabilized Khmer water networks. If true, Wat Ek Phnom may represent not just an engineering achievement, but evidence of how even highly advanced civilizations can become vulnerable when environmental systems exceed their ability to adapt. The temple's decline remains strangely silent. Unlike many ancient cities destroyed by invasion or fire, Wat Ek Phnom appears to have faded gradually. Jungle growth overtook structures, maintenance ceased, religious centers shifted elsewhere. No massive battlefield debris or widespread burn layers clearly explain abandonment. It was as if the civilization sustaining the monument slowly lost the capacity to preserve it. Do you think the Khmer Empire lost ancient engineering knowledge that modern science still cannot fully explain? Share your thoughts in the comments below. Hatnub lies deep within the eastern desert of Egypt, roughly 20 kilometers from the Nile Valley. 4,500 years ago, workers entered this barren landscape to extract one of the most prized materials in the ancient world, Egyptian calcite alabaster. What they left behind may be one of the most important clues ever discovered about how the civilization of the pyramids truly moved massive stone. The site had been known since the 19th century, but the most shocking discovery came in 2018, when archaeologists uncovered a massive ancient ramp system carved directly into the quarry floor. At first glance, it looked simple. Then engineers began calculating its angle. The central ramp was far steeper than historians believed ancient Egyptians could realistically use to drag multi-ton blocks uphill. Along both sides were staircases lined with symmetrical holes once used for wooden posts. The arrangement suggested something extraordinary. The workers may have threaded ropes around these posts to create a primitive mechanical advantage system capable of multiplying pulling force. For decades, pyramid theories struggled with one fundamental problem. A limestone block weighing 2 to 3 tons can already require enormous manpower to move across flat ground. Some granite blocks in the Great Pyramid complex weighed more than 70 tons. Traditional models proposed long, shallow ramps with gradients under 10% because anything steeper would become physically impossible. But the Hatnub ramp appears to exceed gradients of 20% in places. That changes everything. Experimental engineers studying the system proposed that teams hauling a sled could pull ropes wrapped around the wooden posts, while workers standing on the staircases acted as stabilizers. The post would reduce slippage and distribute tension more efficiently across the hauling system. In effect, the Egyptians may have created a crude but highly effective force amplification device thousands of years before classical pulley systems became widespread. Some researchers compared the concept to a capstan mechanism used in later maritime engineering. The implications are enormous. If the Hatnub system worked as intended, then ancient Egyptian labour efficiency may have been dramatically underestimated for over a century. It would mean pyramid-era engineers possessed an advanced practical understanding of friction, load distribution, counterforce, and traction mechanics. Not theoretical mathematics in the modern sense, but applied engineering refined through generations of experimentation. Even more mysterious is the material they were extracting. Hatnub alabaster is beautiful but extremely fragile. Unlike granite, which fractures violently under force but remains structurally hard, calcite alabaster is softer and highly prone to cracking under uneven stress. Yet many surviving Egyptian alabaster vessels, statues, sarcophagi, and temple furnishings were carved from remarkably large intact blocks. Some pieces display surfaces so smooth and symmetrical that modern observers often underestimate how difficult the raw extraction process actually was. To quarry large alabaster blocks without catastrophic fractures would have required extraordinary control over pressure distribution. Copper tools alone should have worn down rapidly. Dolerite pounding stones could break material away, but uncontrolled impact risks sending invisible fractures through the stone. Modern quarry operations rely heavily on steel cutting systems, controlled vibration management, and precision separation techniques. The Egyptians had none of these, yet Hatnub produced luxury stone for centuries. Archaeologists studying extraction marks at the site noticed long linear cut traces and surprisingly controlled fracture lines. Some researchers believe quarry workers intentionally exploited the natural bedding planes of the calcite deposits with a level of geological understanding rarely associated with Bronze Age civilizations. Others argue that ancient craftsmen may have used lubrication techniques involving water or oil to reduce stress during separation. No consensus exists. Then there is the logistical problem. Hatnub sits in an arid desert environment where summer temperatures can exceed 40 degrees Celsius. Maintaining a permanent industrial operation there would have required enormous organization. Inscriptions at the quarry mention expeditions composed of administrators, scribes, stoneworkers, transport crews, and supervisors. Some expeditions likely involved hundreds of laborers operating simultaneously. This challenges the outdated image of pyramid construction as chaotic slave labor. Modern archaeological evidence increasingly points toward highly organized state-managed labor systems with food distribution, housing networks, medical care, and rotational workforce planning. At Hatnub, workers had to transport water, timber, rope, tools, and food deep into the desert, while simultaneously hauling massive stone blocks back toward the Nile. The rope technology alone raises questions. Plant fiber ropes deteriorate rapidly under desert heat and repeated heavy strain. Yet the hauling systems implied at Hatnub would have subjected ropes to extreme tension loads, potentially exceeding several tons per line. The Egyptians somehow maintained enough material reliability to operate quarry networks continuously for generations. Some surviving ancient rope fragments from Egypt demonstrate surprisingly sophisticated weaving structures, but the full engineering limits of these materials remain poorly understood. The desert roads surrounding Hatnub add another layer of mystery. Satellite analysis and archaeological surveys suggest that many quarry routes were not random tracks worn into the landscape, but carefully selected transport corridors optimized to minimize slope variation and maintain sled stability. Certain road segments appear intentionally reinforced with compacted surfaces. In some areas, ancient workers may even have modified terrain to improve transport efficiency. This aligns with another controversial discovery connected to Egyptian transport technology. Tomb paintings from the 12th dynasty depict workers dragging colossal statues on sleds while another individual pours liquid in front of the sled runners. In 2014, physicists from the University of Amsterdam demonstrated experimentally that slightly wet sand can reduce drag force significantly by increasing the rigidity of the sand surface. Under ideal moisture conditions, pulling resistance may drop by nearly 50%. Combined with the Hatnub ramp system, this suggests Egyptian engineers were not relying on brute strength alone. They may have systematically manipulated environmental physics to move impossible loads with maximum efficiency. And yet major questions remain unanswered. Why is physical evidence for similar ramp systems so rare if they were essential to pyramid construction? Why do many reconstructed pyramid theories still fail to account for the speed at which massive royal complexes were completed? The Great Pyramid alone contains an estimated 2.3 million stone blocks. Even assuming a 20-year construction period, workers would have needed to position roughly 300 blocks per day. Some researchers argue the logistics border on industrial-scale production. Hatnub may provide a missing piece of that puzzle. Instead of imagining pyramid construction as primitive labor amplified by sheer manpower, the evidence increasingly points toward a civilization that mastered practical engineering through observation, repetition, and incremental optimization over centuries. Their systems were not powered by advanced machines in the modern sense, but they may have been far more mechanically sophisticated than traditional history once allowed. The quarry inscriptions also reveal something psychologically important. Many workers left behind names, expedition records, prayers, and statements of achievement. These were not anonymous masses blindly hauling stone. They were organized specialists participating in state engineering operations on a scale unprecedented in the ancient world. Do you think Hatnub finally explains how the pyramids were built? Or does it prove the ancient Egyptians possessed engineering knowledge far beyond what historians still accept? Share your thoughts in the comments below. Buried within the dense forests of Campeche in southern Mexico, Hochob Archaeological Zone remained concealed beneath vegetation for centuries before modern archaeological surveys began documenting the site in the 20th century. The name Hochob roughly translates to place of the ears of corn, yet the city became known for something far more mysterious. Massive stone temples decorated with giant monster-like facades, unlike almost anything else in the Maya world. Unlike famous Maya centers such as Chichen Itza or Tikal, Hochob was built inside remote tropical terrain with no major rivers nearby and no obvious transportation network capable of supporting large-scale construction. Yet archaeologists discovered multi-room palace structures, ceremonial buildings, vaulted corridors, and enormous decorative facades constructed with astonishing precision. The deeper researchers investigated the site, the more Hochob began to look less like a forgotten jungle ruin and more like a technological puzzle left behind by the ancient Maya. The most iconic structures at Hochob are the enormous zoomorphic temple entrances, gigantic stone masks representing supernatural beings whose mouths form the doorway into the temple itself. These facades are composed of hundreds of carefully shaped limestone blocks fitted together with remarkable accuracy. What makes this mysterious is the level of precision achieved without iron tools, steel blades, cranes, or modern measuring equipment. Some joints between stones are so tight that even thin blades struggle to slide between them. Engineers comparing the stonework to later medieval masonry have noted similarities in precision, despite the Maya lacking metal-cutting technology available in Europe centuries later. The limestone used at Hochob is softer than granite, but that alone does not explain the consistency of the cuts. Researchers examining the surfaces discovered evidence of repeated abrasion polishing and controlled shaping techniques that would have required enormous labor coordination. Even more puzzling, many decorative sections appeared geometrically symmetrical across large surfaces, implying the builders possessed advanced planning systems and standardized measurement methods. Several archaeologists have suggested the Maya may have used chord-based geometric grids or proportional systems similar to those later documented in other ancient civilizations. Yet no surviving written technical manuals from the Maya world explain how such massive symbolic facades were designed and assembled so accurately in dense jungle conditions. One of the strangest engineering mysteries at Hotchob involves its surviving stucco surfaces. Tropical environments are among the worst possible places for exposed limestone architecture. High humidity, seasonal rainfall, heat, biological growth, and expanding tree roots rapidly destroy exposed structures. In many tropical regions, unprotected stone can degrade severely within centuries. Yet parts of Hotchob's stucco decoration have survived for over 1,000 years. Scientific analysis of Maya lime plaster from sites across the Yucatan Peninsula revealed evidence of sophisticated material processing. To produce lime plaster, the Maya heated limestone to temperatures approaching 800–900 degrees Celsius before mixing it with water and additives. Maintaining such temperatures consistently would have required highly organized fuel systems and advanced control of combustion environments. Researchers studying Maya plasters discovered traces of organic compounds, plant extracts, and mineral particles that may have improved water resistance and structural durability. Some modern materials scientists compare these mixtures to experimental self-healing lime mortars, where microscopic chemical reactions allow small cracks to reseal over time through calcite recrystallization. At Hotchob, the survival of detailed carvings despite centuries of tropical storms suggests the builders understood environmental engineering at a surprisingly advanced level. Some walls appear capable of shedding water efficiently due to subtle surface angles invisible at first glance. Others show evidence of layered finishing techniques designed to reduce moisture penetration. The mystery becomes even greater when compared to many later colonial structures in tropical America that deteriorated far more rapidly despite access to metal tools and later construction methods. Modern engineers consider tropical limestone terrain extremely difficult for long-term heavy construction. The porous bedrock absorbs water, fractures easily, and shifts over time. Yet Hotchob's buildings remained standing through centuries of storms, erosion, and environmental pressure. Archaeological surveys suggest the Maya may have constructed multi-layered foundations using compacted rubble, crushed limestone, and drainage materials to distribute weight across unstable ground. This resembles principles used in modern geotechnical engineering. What astonishes researchers is the scale of the achievement. Some structures at Hotchob weigh thousands of tons collectively, yet they show surprisingly limited subsidence compared to expectations for tropical terrain. Without reinforced concrete, steel frames, hydraulic excavation equipment, or modern soil analysis, the Maya somehow created stable ceremonial complexes capable of surviving for centuries. Comparisons are often made to other ancient civilizations that mastered difficult terrain, such as the Inca foundations at Machu Picchu or Roman harbor engineering along the Mediterranean. But unlike the Romans, the Maya worked without limpozzolana concrete capable of hardening underwater. Unlike the Inca, Hotchob existed in humid jungle conditions that accelerate structural decay dramatically. This raises a disturbing possibility. The Maya may have possessed generations of accumulated empirical engineering knowledge far beyond what survives in the archaeological record. Hotchob also contains large corbel vaulted chambers, a hallmark of Maya architecture. Unlike true arches, corbel vaults are formed by stacking stones progressively inward until they nearly meet at the top. Structurally, this method creates enormous lateral pressure and instability. At Hotchob, some vaulted corridors appear unusually wide relative to their supporting walls. Modern structural simulations suggest several chambers approach dangerous load thresholds if constructed purely through basic trial-and-error methods. And yet many of these corridors survive for centuries. This suggests Maya architects deeply understood weight distribution, compression forces, and structural balance even without formal mathematical physics. Some researchers believe Maya builders refined their techniques over generations through repeated experimentation across cities in the Pus-and-Chens regions. The precision becomes especially mysterious considering the environmental conditions. High humidity weakens mortar, biological growth damages joints, and seasonal thermal expansion stresses stone structures continuously. Even so, parts of Hochob's vaulted architecture remain intact long after many younger historical buildings collapsed elsewhere in the world. Several structures at Hochob appear aligned with solar events, especially equinox and solstice positions. This is not unique among Maya cities, but the consistency of the orientations has generated debate among archaeologists. The Maya possessed one of the most advanced astronomical traditions in the ancient world. They accurately tracked Venus cycles, solar years, eclipses, and complex calendar systems. However, the precision implied at sites like Hochob raises difficult questions. How did observers in dense jungle terrain achieve such consistent alignments without telescopes or precision optics? Some theories suggest the Maya established long-term observational stations using horizon markers and repeated generational measurements. Others argue they may have used architectural sightlines integrated into ceremonial spaces. Comparisons are often drawn to solar alignments at Stonehenge or the astronomical planning of ancient Egyptian temples near Karnak. Yet Hochob's alignments were achieved in a tropical environment where vegetation growth constantly obstructed long-distance visibility. This makes the consistency even more difficult to explain. Perhaps the greatest mystery surrounding Hochob Archaeological Zone is logistics. The city was built deep inside tropical jungle with no major rivers nearby, while the Maya did not use large draft animals or practical wheeled transport for massive construction projects. Yet thousands of tons of stone were still quarried, moved, and assembled into enormous structures. Simply transporting multi-ton limestone blocks through hot, humid jungle conditions would have required extremely complex labor coordination. Researchers estimate that major Maya cities demanded millions of labor hours to complete large construction projects. The real mystery is not only how the Maya built Hochob, but how they maintained such a precise logistical system in one of the harshest environments imaginable. Do you think the Maya truly possessed engineering knowledge far beyond what history tells us? Share your thoughts in the comments below. Southeastern Attica, Greece. Archaeologists excavating the hills near the ancient silver mines of Larion uncovered the remains of Thorikos, a mining and industrial settlement that operated for more than 3,000 years. Beneath the dry rocky terrain, researchers found collapsed shafts, underground tunnels, ore washing systems, furnaces, and one of the oldest known Greek theatres. What shocked historians was not the city itself, but the scale of engineering hidden underground. Thorikos looked less like a normal ancient settlement, and more like an early industrial complex centuries ahead of its time. The greatest mystery of Thorikos is its enormous subterranean labyrinth. Surveys have revealed dozens of kilometers of tunnels cut directly into hard rock, many descending over 100 meters below the surface. Some shafts are barely 50 centimeters wide, forcing miners to crawl while following tiny veins of galena, the lead ore containing silver. Modern mining engineers have questioned how ancient workers could maintain such accurate directional excavation without modern surveying tools, electric lighting, or oxygen systems. Even today, tracing narrow mineral veins underground is difficult using laser mapping and geological scanners. Yet Thorikos miners somehow followed these veins with astonishing precision. Some tunnels appear deliberately angled to intersect natural airflow currents. Archaeologists discovered vertical shafts that seem almost useless for ore transport, but highly effective for ventilation. Experiments conducted in reconstructed tunnels showed that temperature differences between upper and lower shafts could create natural air circulation similar to passive ventilation systems used in modern architecture. This has led some researchers to argue that Greek miners possessed a practical understanding of airflow dynamics long before formal physics existed. Without proper ventilation, miners would have quickly died from oxygen depletion, smoke inhalation, and toxic lead dust. The fact that the mines operated continuously for centuries suggests the system worked remarkably well. Near the mines, archaeologists uncovered massive ore washing facilities unlike anything expected from the ancient world. These installations contained channels, settling tanks, filtration basins, and carefully angled stone floors designed to separate silver-bearing minerals from crushed rock using flowing water. The engineering precision is difficult to explain. Some channels maintain gradients so consistent that modern hydraulic engineers compared them to controlled sedimentation systems. Water velocity had to remain slow enough for dense mineral particles to sink while lighter debris washed away. Researchers studying the installations found waterproof plaster coatings still partially intact after more than 2,000 years. Chemical analysis suggests the builders mixed lime with volcanic or silicate-rich materials that created unusually durable surfaces resistant to erosion and mineral corrosion. The strange part is efficiency. Ancient Athens became one of the wealthiest powers in the Mediterranean, largely because of Laurian silver production. Historical records suggest enormous outputs of silver coins, enough to finance fleets, armies, and infrastructure projects. Yet experimental archaeology indicates that traditional ancient methods should not have been capable of extracting silver at such high yields. Some metallurgical researchers believe the workers at Thorikos may have used refined processing techniques that were never fully recorded in surviving texts. Entire sections of their industrial knowledge may simply have vanished. Separating silver from lead required a dangerous process called cupellation, or had to be heated to temperatures exceeding 900 degrees Celsius while maintaining carefully controlled oxygen levels. Too little oxygen and impurities remain trapped in the metal. Too much heat and valuable silver could be lost entirely. Excavations at Thorikos uncovered furnace remains and slag deposits containing crystal formations that only develop within very narrow thermal ranges. This implies ancient metallurgists somehow maintained surprisingly stable furnace temperatures for long periods. That level of heat control is astonishing considering they had no thermometers, modern refractory ceramics, or industrial insulation. Researchers comparing the slag structures found similarities with much later Roman metallurgical systems, despite Thorikos operating centuries earlier. Some theories suggest the furnaces used highly specialized airflow channels or bellows systems, capable of creating controlled combustion environments. Others argue that generations of trial and error experimentation allowed craftsmen to recognize exact temperatures through flame color, sound, and metal behavior alone, but no surviving Greek technical text fully explains the process. The silver industry at Thorikos should have consumed unimaginable quantities of wood. Cupellation requires intense and prolonged heating, meaning thousands of furnaces operating over centuries would have devoured forests across Attica. Researchers estimating fuel consumption concluded that millions of trees may have been required to sustain the industry. Yet paleo-environmental studies around Laurion do not perfectly match the scale of deforestation expected from such industrial activity. This contradiction has become one of the site's strangest mysteries. Did ancient metallurgists develop furnaces far more fuel-efficient than historians assume? Did they use charcoal production methods now lost to history? Or did they exploit alternative combustible materials not yet identified archaeologically? No excellent explanation fully resolves the discrepancy. Evidence from Greenland ice cores revealed unusually high atmospheric lead pollution during periods of peak Greek and Roman silver production. Scientists detected spikes in airborne lead particles dating precisely to the era when Lorien mines were most active. This means Thorikos was not a small mining settlement. It was part of one of the largest industrial pollution events in the ancient world. The consequences must have been devastating. Lead poisoning affects memory, coordination, fertility, and behavior. Miners, smelters, and even nearby populations were likely exposed to toxic contamination for generations. Some historians believe the economic power of Athens may have been built partly on a hidden human catastrophe occurring beneath the ground. Thousands of enslaved workers labored in suffocating tunnels surrounded by toxic dust and furnace smoke. Ancient writers occasionally described Lorien miners as ghost-like figures emerging from underground darkness covered in ash and metal residue. The descriptions sound disturbingly similar to workers from 19th century industrial coal mines. Thorikos and Lorien may have directly changed world history. In 483 BCE, a massive silver discovery in the mines allowed Athens to construct approximately 200 triremes, advanced warships that formed the backbone of the Greek fleet during the Battle of Salamis in 480 BCE. That battle stopped the Persian invasion and preserved the independence of Greek civilization. Without Lorien silver, classical Athens may never have become the center of philosophy, democracy, mathematics, and art. In other words, the intellectual foundations of Western civilization may have depended on an underground industrial machine powered by mining technology still not fully understood today. One of the most disturbing mysteries surrounding Thorikos is how little technical documentation survived. The Greeks recorded philosophy, geometry, politics, and astronomy in extraordinary detail, yet the engineering methods behind Lorien's mining empire remain strangely absent. Many historians suspect the knowledge was transmitted orally between skilled craftsmen and mining specialists rather than written openly. Once the mines declined, entire generations of industrial expertise may have vanished forever. This pattern appears repeatedly throughout ancient history. Complex technologies emerge, operate successfully for centuries, and then disappear almost without explanation. Roman concrete survived underwater for 2,000 years before modern scientists understood why. Damascus steel vanished despite its legendary strength. Greek fire burned on water, yet its formula was lost. Thorikos may belong to the same category, a forgotten technological system whose full capabilities disappeared long ago. What do you think the miners of Thorikos were really searching for deep beneath the earth? Silver alone, or something far more mysterious? Share your thoughts in the comments below. Copper was not supposed to exist here. Not this early. Not in a small Neolithic settlement hidden in the hills of eastern Serbia. Yet beneath the soil of Belovodi archaeological site, archaeologists uncovered evidence that humans were extracting metal from stone nearly 7,500 years ago, more than 1,000 years before the rise of the first Great Bronze Age civilizations. The discovery forced historians to question one of the oldest assumptions in archaeology, that advanced metallurgy began in the Near East and slowly spread into Europe afterward. Belovodi was excavated as part of research into the mysterious Vinca culture, a Neolithic civilization that existed across the Balkans between roughly 5,700 and 4,500 BCE. During excavations, researchers discovered fragments of copper slag, furnace debris, burned ore, and vitrified clay surfaces. Radiocarbon dating placed some of the material around 5000 BCE, At first, many archaeologists assumed contamination or natural burning, but laboratory analysis confirmed something astonishing. The inhabitants were intentionally smelting copper ore. That date changed everything. Before Bellovode, the standard timeline placed the birth of metallurgy in Anatolia and Mesopotamia around the late 5th or 4th millennium BCE. Bellovode pushed organized copper smelting significantly further back in time and deep into prehistoric Europe. The greatest mystery surrounding Bellovode is not simply that copper existed there. It is that the people living at the site appear to have understood a highly complex industrial process, long before historians believed such knowledge was possible. Melting pure native copper is relatively simple, and small pieces can accidentally melt inside pottery kilns. But Bellovode shows evidence of something far more advanced, extracting copper from ore through controlled smelting. That process is enormously more difficult. Copper ores such as malachite or azurite must be heated to temperatures exceeding approximately 1080 degrees Celsius. Reaching that heat consistently in the Neolithic period should have been extremely challenging because ordinary open fires cannot maintain such temperatures for long, and even many early furnaces from later periods struggled with thermal stability. To achieve this, the Vinca people needed a furnace capable of retaining extreme heat, controlled oxygen flow, proper charcoal-fuel ratios, knowledge of ore preparation, and timing precise enough to separate metal from waste material. This is what makes Bellovode so controversial. Archaeologists are not looking at a lucky accident. They are looking at a technological system. Compared to other Neolithic communities in Europe, the gap is staggering. Many settlements from the same period were still using polished stone axes and bone tools almost exclusively, while Bellovode's inhabitants were experimenting with pyrotechnology sophisticated enough to alter the atomic structure of rock. Even more confusing is how suddenly the technology appears. Normally, industrial innovation develops gradually over centuries. Pottery becomes hotter, kilns improve, experiments increase, and metallurgy slowly emerges. But at Bellovode, the evidence suggests people already understood the fundamentals surprisingly early. The transitional stages are largely missing. Some researchers compare this leap to finding a functional steam engine in a medieval village centuries before the Industrial Revolution. One of the most disturbing technical mysteries involves the furnaces themselves. Fragments of clay found at Bellovode show signs of vitrification, a transformation where clay partially melts into a glass-like substance due to prolonged exposure to extreme heat. In some areas, the thermal damage suggests temperatures exceeding 1100 degrees Celsius. That raises an uncomfortable question. How were Neolithic people controlling heat with such precision? Most reconstructions of primitive furnaces struggle to maintain those temperatures consistently without advanced airflow systems. Yet no surviving bellows, metal pipes, or mechanical air systems have been found at Bellovode. Some archaeologists believe the Vinca may have used underground draft furnaces, while others propose natural wind tunnels built into hillside structures. A few experimental archaeologists managed to reproduce similar temperatures, using carefully engineered clay furnaces combined with charcoal and ceramic air nozzles. But these experiments required extraordinary precision and repeated failures. In other words, Bellovode's metallurgy may have depended on generations of accumulated technical knowledge that left almost no trace behind. The mystery becomes even deeper when compared to Egypt. Around the same period, Egyptian communities were still primarily working with stone, flint, and limited ornamental copper. Large-scale controlled smelting would not dominate the region until much later. Yet in the Balkans, an apparently isolated Neolithic society was already manipulating ores at industrial temperatures. Chemical analysis of slag and ore fragments revealed something remarkable. The people of Bellovode did not use random stones. They selected specific copper-rich minerals with unusually high efficiency. Many samples contain malachite and azurite, minerals identifiable by their bright green and blue coloration, but color alone does not explain the sophistication of the process. The ore was often crushed into smaller particles before heating. This dramatically improves oxygen exposure during smelting and increases metal extraction efficiency. That detail matters because it suggests an understanding of process optimization rather than primitive experimentation. Researchers also discovered that some ore sources likely came from locations several kilometers away. This implies organized mining expeditions or trade networks capable of transporting heavy mineral loads. The Vinca culture may have possessed one of the earliest specialized resource economies in Europe. That possibility changes the image of Neolithic societies entirely. Rather than isolated farming villages, Bellovode may represent a proto-industrial community where certain individuals specialized in metallurgy while others managed agriculture, transport, or construction. Another disturbing clue emerged from environmental studies around the region. Sediment analysis revealed elevated concentrations of heavy metals consistent with prolonged copper smelting activity. Tiny traces of contamination appear embedded in ancient soil layers dating back thousands of years. This suggests Bellovode was not conducting occasional experiments. The process may have operated repeatedly for generations. If true, the site could represent one of humanity's earliest examples of industrial environmental impact. The implication is extraordinary. 7,000 years before factories darkened the skies of 19th century Europe, prehistoric metallurgists in the Balkans may already have been altering local ecosystems through chemical pollution. Some scientists argue the scale was still small compared to later Bronze Age operations, but the principle remains the same. Humans had begun transforming the environment through industrial heat and metallurgy far earlier than expected. The Vinca civilization remains one of the great mysteries of the Neolithic world. Their settlements were unusually large for the time, with some containing thousands of inhabitants, along with strange symbols carved into pottery that many researchers believe may represent a form of proto-writing. But by the end of the 5th millennium BCE, many Vinca settlements declined or were abandoned. Metallurgical activity decreased, trade networks collapsed, and much of their technological knowledge appears to have vanished with them. This creates one of Bellovode's biggest mysteries. How could such advanced metallurgical knowledge disappear? Some researchers believe copper smelting consumed enormous amounts of charcoal, leading to severe deforestation. Others point to climate change or social collapse. But another possibility is even more unsettling. The knowledge may have belonged only to a small group of specialist metal workers, and when they disappeared, the technology disappeared with them. What do you think happened to the lost metallurgical knowledge of the Vinca civilization? Was it destroyed by collapse, forgotten over time, or hidden within a small group of ancient specialists? Share your thoughts in the comments below.